I have rolled my sleeves up for this lesson because it is a big deal. It's a big deal. And it's going to be awesome. But why? Why do we have double integrals and polar coordinates? It's a thing. Why? Why? 2 reasons. This is not to make your life harder, even though you're going to think that. It's to make some integrals easier. It's to make some integrals possible. Because we can't do it over rectangular. I will give you the main statement for this entire lesson. If the regions you have to work with are circular, use polar. If the region you have to work with are lines and rectangles, use rectangular. What we did in the last section is rectangular. What we're doing now is polar. Polar defines circles really, really nicely. Really nicely. Because it takes that x squared plus y squared thing, which gives us circles, and makes it r squared. And that is just genius. So we can translate a lot of our circular regions into stuff with polar coordinates. Is it hard? No. The only hard part that we're going to have, there's 2 hard parts. 1, you got to change everything into polar. 2, you got to draw the regions. As soon as you draw the regions, you're good. And sometimes you don't even have to do that. I'll show you how to cheat occasionally. But most of the time, we just draw the regions. They're easy anyway. So do you guys understand the impetus for kind of doing this here? It's going to make our lives easier, trust me. Now, there's a little background that we got to get started. If we're going to understand polar coordinates, we need to understand what type of regions we have. So let's take a look at it. Polar coordinates work this way. Polar equations work this way. We have an angle, and we traverse across to another angle, and we have 2 functions. We have an angle, we traverse across another angle, and we're between 2 functions. Only the functions are r equals some function of theta, like every single time. So, if you look at it, according to polar coordinates, these are actually rectangles. Rectangles are defined this way. We're between 2 constants in one direction and 2 constants in another direction. That's how we created rectangular regions. Well, look at our polar. Constant angle, constant angle. Constant radius, that's a circle. Constant radius, that's a circle. That is a polar rectangle. Now we can get a little bit crazier, but we can't get crazier with our angles. Our angles are fixed, so we're between 2 angles. That's going to say something. I'll say it right now. Hope you're listening. That's saying something. If our angles are always between 2 constant values, listen, we have double integrals, right? Right. If our angles are always between 2 constant values, and constants are always on the outside integral, are you tracking with me? Then we have to have d theta on the outside of our integral every single time, because the thetas are equal to constants every single time. That makes things nicer already. There is no guesswork between dx, dy, dx. It's always integrate across the r first, and then integrate across theta. Theta is always last. Why? Because theta is always between constants. The functions we go between for our radius across this region, that can change. I know I'm just talking a lot at you. I'm trying to throw it all at you right now, and then we're going to explain it as we go. So the main ideas here are, we have the same sort of ideas for regions. It's just that rectangles look a little different between constants, and functions look a little different between polar functions. But the key was, your angle is always between constants. If we're doing double integrals and your constants always have to be the outside angle, or outside integral, then your angle is the thing that creates the outside integral every single time. And the theta that gives you the angle is always the thing we integrate last. Do you guys get it? Let's do a little bit more work then. How? How do we go about changing these from rectangular to polar? Same way we always have. That doesn't change. So when we have normally we get this. We get a double integral over a region, a function x and y. We get dA. But we know a couple things. We now know that r cosine theta represents x. Do you recall this? It's been a while. That's why we did 11.6. If you need a refresher, you go watch 11.6. R sine theta. We also know that x squared plus y squared equals r squared. We also know that tangent theta equals y over x. Those were exactly the things that allowed us to go from rectangular to polar, and they're exactly the same things that are going to let us go from a normal double integral in rectangular coordinates to a great in double integral in polar coordinates. And now if you're still okay with me. So what do they look like? Well, we're going to have two cases. I put case 1 and case 2. Case 1 is the case where we are finding the volume over a polar rectangle, and case 2 is where we're finding the volume of a general polar region. And here's how those things would look. Number one, I really want you to get this concept. Notice that if our angles are constant, then I'm gonna have to have the constant on the outside integral no matter what. Does that make sense? No matter what. I'm gonna have to have theta and theta, theta and theta. I'm gonna have to have those on the outside because those are the only things that are always constant for me, and they're always constant. That's kind of cool, right? So we go, okay, well, how about that? Theta would go from alpha to beta, alpha to beta. We go counterclockwise, just like you normally go in positive angular direction. Start at alpha, get to beta, start at alpha, get to beta. And now if you're okay with that one. Now, let's talk about what we do here. So, do you remember how for any region, I told you, hey, you got to go along one axis first and then go along the other one, and we drew that arrow and the dotted lines. You remember that last time? We're going to do the same thing, but here's what I was just explaining to you. If the angles are always the last thing we do, there's no guesswork about which axis we go down first. We always do things in this order. We always go across the region along the radius, so in the radius direction. So from the origin, we go, okay, hey, you guys pay attention? From the origin, go through the middle of this arc here. Go through the middle. Where do we start hitting this region? Well, we start hitting it at r equals a. Do you see it? We're going to traverse this until we hit r equals b. We're going to hit r equals a and go until we hit r equals b. Well, this is the same thing. It's just the region goes, well, okay, well, our angles are still fixed, no problem, alpha, alpha, beta. But if I go along right to the center of it, I'm going to now hit, what if it's not a constant radius? What if it's like a function? Can I still hit it? Yeah, it's just I'm not hitting a constant. I'm not hitting r equals a. That would be a rectangle. Now it's like you're going between two functions of y or between two functions of x. Notice the similarity. You always have to go between your functions first and your constants last. Are you listening? That's kind of an important concept. You always go between your functions first and your constants last. Since polar functions are always defined in terms of theta, the r equals stuff is always your function. We're always going that direction first. So, okay, let's go hit our function, end at our final function. This would be some function in thetas, and we'd end at some other function in thetas. Now wait a second. Where else are we traversing? Well, we have to traverse each region in two directions, across functions and across constants. So we traverse from r equals a to r equals b, and then secondly, we go from our constants. That's what this represents from alpha to beta. We traverse along our functions first, and then we traverse across our constants. That's what this says from alpha to beta. So I want to put this all together, at least talking about the region. Do you guys see the differences? Here's the key points for you. Do you see the differences between polar rectangles and regions that are not polar rectangles, general regions? Do you see the similarity that in both cases, my alpha are constant alphas, one angle and another? Do you get the idea that with any double integral like ever, our constants are always the last thing that we integrate? The first integral is the last one that we actually do, the outside integral. So how we do it, we go, okay, go between our functions first, That's our first integral. Then go between our constants, which are always thetas. Go between our functions, that's our first integral. Then integrate across our constants, which is always our thetas. That is how every polar double integral is set up forever. Should Vince feel okay with it? Now, things have to happen with this. We have to change this. Because if I'm dealing with r's and thetas, I don't have x's and y's anymore. Can I change x's and y's into r's and thetas? See Exhibit A. You have done that already. So what's our function going to look like? Instead of a function of x, y, ladies and gentlemen, come on, help me out here. What's x equal in terms of polar equations? So we're going to have a function of x and y. We're going to have this a function of x and y. Let's please get this straight. This function had nothing to do with the region. Understood? This function has nothing to do with the region. It's over the region. We're still doing the same thing. We're finding this region on a plane. Verify. It's still on a plane. We're finding some sort of surface over the plane and finding the volume under that surface over the region. It's just we're using polar because polar coordinates translates circles really, really nicely. And our regions here are going to be circles, circular things, cylinders, circles, stuff like that. Does that make sense to you? Okay, so region, we've now conquered that. We go between functions of r, then constants of theta. Functions of r, then constants of theta. It means our integrals are always in the same order. We always do r's first, then thetas. Are you clear on that one? So put it together. You know it from last time. So what's the first thing? Leave yourself some space, please. This is key. But what's the first thing I have to integrate? Is it going to be the dr, dx, dy, or d theta? What's the first thing? This has to match that. Remember? It's got to. So I'm going across the r. Let's call it the r. It's not an axis, but r axis, r direction. R direction first. That's what we did here, guys. We went along the r, along the radius first. We went along the r, along the radius first. We hit two functions of r equals stuff. First, what's the last thing that we should have? Is that ever going to change? No, because the theta is the only thing that's always constant. So we hit the functions of r along the r, hit the functions of r first, then we went theta to theta, theta to theta, theta to theta. It's got to match up. Let's verify it matches up. I'm going to have r equals, the r equals matches up the dr, the first thing. This is going to equal a whole bunch of stuff in theta because polar functions work that way. When I plug in functions of theta, though, it's all going to match up to the second integral. Do you guys see the similarity between this and the double integrals you just kind of conquered? There's only one more thing. Firstly, I've explained it in a way that you can understand it. Understand where it's coming from. Do you understand you never switch these? That's kind of cool. There's one more thing. Some of you guys need to unzone. Some of you guys took your zone out pills today. I can tell. Zone in. Take your zone in pills. I don't even know what those are. But zone in right now. You're going to forget this. You're going to forget this. You're going to forget this from time to time. I'm going to look each of you in the eye right now. Some of you won't. You're going to forget this from time to time. Ramiro, open your eyes. Okay, there you go. You're going to forget this from time to time. You're going to forget this from time to time. You're going to try not to. There's always an r that gets put into your double integral right before the dr. dA becomes r dr. RDR, RDR, these are fun. Okay, that's dorky. RDR d theta, hardy har. That's hardy d theta. But that's about what it is. You always get the R. Are you going to forget the R?
Yes.
Hopefully not now. But it might happen from time to time. It's something that gets put in every double integral when we switch from rectangular to polar. It gets put in there every single time. without fail. Is it easy to forget? You better believe it. Do you think it's going to mess with your integral? It's the first variable that we integrate with respect to. It's going to mess up your integral unless you get that thing right. Does that make sense? Do you want to see where it's coming from? What the R? What's that from? Here's the way I'm going to explain it to you. I can also do this with something called the Jacobian, which is a way that you change variables in these things. We can do that in 14.8 when we actually get there. Right now I'm going to give more an intuitive approach. Here it is. We're going to do it from 1, but it's you can do it with case 2. Do you know that the area of a sector is 1/2 r squared theta? Do you know that? If you don't, that's the area of a sector. You take 1/2 times the radius squared times the theta that we sweep out. That's what happens here. If you want to write this down, fine. If not, I don't care. That's the area of a sector. I just want you to understand where it comes from. Well, if I'm from here, then the area of this region would be the big sector minus the little sector. Do you guys see it? The area of this region would be the area of the big sector. Sector is a part of a circle, okay? Area of the big sector minus the area of the little sector. You with me? The radius of the big sector is B. The radius of the little sector is A. You with me? Okay, so for case number 1, the area would equal 1/2 the big radius. I'm going to talk about the theta in a second. Minus 1/2 the little radius squared. Is that okay? Now, we need something for the theta, what the theta is, and I'm going to do it this way. I need you to keep in mind that we're talking about the calculus behind this. So what we're talking about is that angular change, that theta, when we're doing the calculus behind it, it's real little. Real little. What I'm talking about here is if theta is the amount we sweep out, theta is the change in theta between alpha and beta. The change in theta is the increment in theta. You guys okay with that? You sure? You sure you're sure? This is area of a sector, no problem, big sector. Delta theta is just the change in theta. Theta, same thing. Delta theta is the change in theta. We're going to start factoring. I'm going to put the 1/2s out front. I'm going to put the d thetas in the back. Do you notice a difference of squares? It seems like it's coming out of nowhere. It's not. Just check this out. I know I'm going to blow your mind here for this. You don't need to write it down. Don't write this down. Just listen. Do you remember in Calc 1 how when you did Raman's sums, you separated an interval into a finite number of segments? Infinite number of segments, and for each segment with equal width, you picked an arbitrary point, x1 dot, xk dot, x whatever dot. And we could pick left, right, center, and it didn't matter. Do you remember that? If you don't remember that, that's from Calc 1. Here's what we're going to do. I want you to look at this. Look at what this means. True or false? If I take any two numbers, add them, and multiply by 1/2, I get an average. True or false? So, if I take this radius and add them and divide by 2, I'm getting the midpoint of that. Does that make sense? I'm going to choose this to be my evaluation point for every polar rectangle, just like I would choose an arbitrary point on this interval to be my evaluation point for every single regular rectangle. This, since that's the average of our, okay, how about this one? Do you verify that whatever this is, it's somewhere between there? Okay, that's going to be our evaluation point. We're going to call this R dot. RK dot is really what it is, but let's call it that. It's an arbitrary point. We are picking the center point, but it's our evaluation point to represent the radius there. Now if you're like, wait a minute, that's right in the middle. Yes, but think about this. If I let that polar rectangle get really, 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 really little, that RK dot is smashed between two radiuses that are coming together like this. They're so close it makes no difference between them. Does that make sense? So I'm using that as my evaluation. It could be anywhere. It doesn't matter. I'm just choosing that one. How about that? How about B minus A? True or false? B minus A is simply the distance between the two radii that I'm evaluating. Well, that would be how much R is changing. That's the increment across our radius. And then we have this delta theta, how much we're changing angle to angle. Do you guys see where all this stuff comes from? All this stuff's, see where all this stuff comes from? Sir? All this stuff comes from, we have an evaluation point. Hey! We have a delta R, how much our R is changing from value to value on a really little rectangle. How much our theta is changing from angle to angle on a really little rectangle. And when you take a limit, as these things approach zero, as the number of rectangles goes to infinity, both of these things approach zero. When these things both approach zero, we go from increment to differential. We get dr. We get d theta, but that turns to r. Do you see? So our volume then, when I integrate, would be the height, the function value, above these little rectangles. But this, when you take a limit, when the number of rectangles goes to infinity, these things get really little. That goes to zero. That's dr. That's what the differential actually means. It means something that's approaching a distance, a width that's approaching zero. That goes to zero. That's what the d theta means. That goes to the evaluation point of any radius, a variable r. This goes to, so when I do the d on both sides. So take the differential on both sides. We get dA. That's what that is r dr d theta. And hopefully that's good enough for a proof to show you where that actually comes from. Why we get the r. Why we get the r is because we pick an evaluation point between the two radii. That's where it comes from. Does that make sense? Now the examples, man. Now we get to the real stuff. I'm gonna try to make your life easier by making it harder at first, but it's gonna end up being easier because when we get done with our first example, I'm gonna say, hey, how would you have done this if you didn't have polar? And then you're gonna see it. Okay, here we go. Let's evaluate this. Let's talk about that. Maybe I'll ask you now. When I don't give you the constants and the functions, what's the first thing you should do, learning from 14.2, first thing you should do with any region, what should you do with it? Ladies and gentlemen, draw the region for these every single time. Draw them every single time. Now, I want you, before you start drawing it, I know I just told you to draw it, but stop for a second. What type of region is this going to be? What's that give you? Circle in your head for a region should just go polar. Just scream out polar. Why? Because if I'm going to draw this thing, which we're going to, Radius of what, ladies and gentlemen, please? In quadrant 1, that gives us radius of 2 in quadrant 1. X equals 0. X equals 0 is still this y-axis. And x equals y or y equals x is that. Or x equals y, doesn't really matter. Now I want you to think about this. Firstly, we got to think about what the region is. What the region is. Look carefully, please. Look carefully. This is all in quadrant 1. Is the region the entire quarter of a circle? Is it the whole quarter of a circle? No, it's bound by that. So it's either the bottom eighth of a circle, half this quarter, or the top. Well, which one is it? It's right here. It tells it to you. Which one is it? The bottom or the top, do you think? Is this x equals 0 this? You have to have the region between all three of these parts, okay? So the region's got to be bound by the circle, check. It's got to be bound by the line, check. That satisfies both. But it also is bound by x equals 0, that's this one. It's this region right there. That's the region we're talking about. So if you feel okay with that one. Now imagine this. Imagine I said, hey, I want you to do this with rectangular. Go along an axis first. Is that going to be super fun? This one's okay. But this you'd have to solve for y. You're going to get some pretty nasty junk out of that. Do you see it? You're going to be substituting in the square root of 4 minus x squared. I don't want to do that. That's crazy. Let's not do that. Let's instead use some polar. How we do it, and we already did the first part. We identify the region that we have. This is our region. That's our region. That segment there. Honestly, the picture will tell you just about everything you need to know. Here's what I'd like to do first. I want to set up the double integral with at least the region part complete. That's how we did this. That's how we're going to do this. That's how we're going to do all of them. We're going to change dA to what it absolutely has to be in the same order that it absolutely has to be in. Then we're going to focus on our function. The setup is the only hard part. You must believe me, the rest of it is integrals you know how to do. You know how to integrate. I know this you do. Let's do the setup. You guys ready for it?
Yeah.
Yeah. Yay! What do we go across first? Every time without fail, do we go angle to angle or do we go radius to radius? Always dr. Always, no matter what. So we always have to go radius to radius. Well, let's do that. Let's start by thinking about how the region is defined. If this is the x squared plus y squared equals 4, then this also means this is simply r squared equals 4 or r equals 2. That's the polar function r. Are you guys okay with that one? X squared plus y squared is r squared. So r squared is 4, r is 2, square root of both sides. Here's what I'd like you to do every single time you draw one of these pictures. Put your pen or pencil on the origin. Put your pen or pencil on the origin. I want you to tell me when you start hitting the region. When you start hitting the region, that's the smallest value of r. And you go through the region. When you hit the furthest value, the furthest r in your region, that's when you stop. So right here, do I start hitting the region immediately? How about this? Some of you guys don't know. If it was this, I would not start hitting the region. I wouldn't start hitting it until I got to right there. Right from the onset, right now, am I already in the region when I start going through? Yes. That means that r starts at what? 0. R starts at 0. So if I want to set this up, I know right off the bat a couple things about it. You know right off the bat a couple things about it. What is dA going to change to, please? Come on, shout it out. I need to know that more than 2 you know it. What's dA going to change to? What is it? Yeah. You can be pirates. It's okay. RDR. No? Nobody likes pirate zombies sometimes? I know that's popular these days. Super cool. R, dr, d theta. Listen, the reason why we go across the region in the R direction first is that is always first. This is always the direction you go through first, which means I need this to be R equals and R equals. Show of hands if you understand that concept. Whatever's first is the direction you're going in first, you have to have R equals. So we start through our axis, along our radius direction. We start intersecting that region immediately. That means R goes to 0, or R goes from 0. Where does it end? Keep in mind it has to be in terms of R, not X and Y any longer. We're going in terms of R. Where does it end? 2. Just a radius of 2. That's why polar's so nice. It changes crazy functions from X and Y into constants. I like constants a lot more better. That's a lot better. So if you feel okay with that one. Now, before we even touch this, I want to end with the d theta. So the first direction is in the R direction. The second direction, I'm going to traverse from my angle to the end of my angle. Starting angle to ending angle, always counterclockwise, same way we always do positive angular motion. It's from here to there. The only issue is, and you know what, the picture is going to tell you, you can kind of intuitively guess what these angles are, but I'll show you mathematically how to do it also. Where does this angle start? Going from here, does it start at 0? Where does it start? Pi over 4. Where does it end? That is the angular motion I'm looking for. Does that make sense? Some of you guys weren't even watching. You should be watching. Do you guys get that the angle I start moving this way is pi over 4? And I end at pi over 2? What if you couldn't just see it? What's the slope of that? The slope is never a variable. The slope is tan theta. Only place tangent equals 1 in the first quadrant. It's pi over 4. It shows you right there. You go, okay, well, wait a minute. What about that one? What about that one? What's the slope of x equals 0? What is the slope of x equals 0? It's undefined. Where is tangent undefined? 2. Shows you what that is. Does that make sense? So slope 1, pi over 4. Slope undefined, pi over 2. You're good. First quadrant, you're good. So we go, hey, d theta's got to be last. That's right. We're always going between constants for our theta. That's fantastic. Where you start counterclockwise is theta equals pi over 4. Where you end is theta equals pi over 2. And you have just done the hardest part of any double integral setup for polar. You've drawn the region and you've set up the double integral. Everything else is going to be downhill from here. In a good way. Downhill, but easily. Should fans feel okay with the setup? Now, let's. Ooh, wait a minute. You need everything to be in R's and thetas. Everything. Fortunately, we got a way to do that. Hey, how much is x equal to? And why? Using those two things, can you translate, and x squared plus y squared equals r, r squared, can you translate any rectangular function into a polar function? Why do you think we did in 11.6? So that you could practice this stuff, so you can get it. So instead of x times y, no, I want r cosine theta times r sine theta. And we didn't forget our r dr d theta, which explained where that comes from. And that looks pretty darn good to me. Did I make it make sense on where this stuff comes from for you, though? So let's double check everything. Do you understand why we're going from 0 to 2? Do you understand why we're going in the r direction first? dr is always first. That r is a variable that we're going to multiply times, just like any other variable. So that's going to be there. dr, r direction first. Do you understand why we're going from pi over 4 to pi over 2? Yes, no? Okay, let me ask you then. Don't change your work, you just listen and watch. What if this was not there? If that constraint was not there, would it change the r? No. Would it change the theta? Would it change that theta? Would I still be ending here?
Yeah.
Yes. Where would I be starting?
0.
What's the slope of 0?
0.
Tangent of 0 is 0. So I'd be going from 0 to if that was not there, I'd be going from 0 to pi over 2. Does that make sense to you? That changes your problem a little bit. Now, hey, what's the next thing you do? Come on, we're now almost home free. What's the next thing that you would do here? What would you do? Before you integrate even? Probably multiply some stuff together. Let's do that. So here we have R to the what? R to the, don't forget about the extra R. We always do our double integrals of polar coordinates dr first, which means r is always our first variable, which means you don't have to worry about this stuff right now. Let's plug it in. Hey, well, not plug it in, sorry, let's do the integral. What would you do if you did the integral of r cubed? Cosine theta, sine theta, those are constants with respect to r. What's the integral of that? Cool, write it down. Hey, ladies and gentlemen, what variable am I about to plug in for r theta? What variable am I always going to plug in for first in polar coordinates? That's kind of nice. So if we plug in 2 first, which we're going to have r to the 4th, that's 2 to the 4th, that's 16 over 4, you should get 4 out of that. Do you guys see where the 4 is coming out of that? The 0 is going to give you 0. That's really nice. Still so far so good? Yes, no, what do you think?
Yeah.
Okay, cool. What's the next step? Next step is you know calculus 1. So go for it. Why don't you try it? Keep in mind you can still change bounds. It's still a good idea. If you do not change bounds, you don't have to, but you have to substitute back in before you evaluate. Me personally, I'm going to change bounds pretty much every single time. Sine u is our u. Cosine theta d theta eliminates this. That's fantastic. We still have a 4 and a u. I'm changing bounds. This goes to 1. This goes to root 2 over 2. And because we did that, because we changed our bounds, we don't have to resubstitute. If you don't change your bounds, then right now you're putting in sine squared and you're evaluating it. It's not a big deal. It doesn't matter which one you do. I really don't care. That's not the point. At this point, we do, let's see. Two times 1 squared minus 2 times root 2 over 2 squared. That's 2 over 4. That's 1/2 times 2 is 1. We get 1. Now, what's it mean? What did we just find? It's the volume of what? That right there is the surface. We found the volume under the surface as bound by this little region, as bound by this sector, is what we found. Would it have been harder to do it rectangular? You better believe it. Because this function is now y equals square root of 4 minus x squared, and that sucks. That's going to be really hard to do. Because that goes here, and your region part, that's not so much funsies, all right? Show of hands if this is making sense to you. You get it. You get the idea. Honestly, for right now, we are just going to practice maybe just like 2 more problems, and then we're gonna call it good on this section, okay? But I want to make sure I at least show you some stuff that is certainly going to be like a test level question for pretty much darn near anybody's test ever written. They're going to put something like this on your paper because it looks really confusing. It is not. It's actually one of the easier things that we do, but you need to see it. So here we go. You know what? It's going to take us a little bit of time. Do you have any questions on this at all? Pretty wordy, right? Find the volume of between that thing and the xy plane as bound by the cylinder of that, crazy. Let's verify a few things about it. Firstly, surface, yes? Surface, 3D surface. Cylinder, does that look like a cylinder to you? X squared plus y squared equals 1 in 3D. Along which axis is this cylinder traveling? Z. Cool, so we have this, if this is xy, we have this surface floating out here. We got this cylinder traveling along the z. That cylinder is going to intersect that surface somewhere in it. It's going to cut that surface. Hey, what shape is the trace of a cylinder like that? So any level curve along that cylinder is going to be a what? Circle. That's what we're looking for. That is going to create a projection onto the xy plane. That cylinder creates our region, and it's a circle. If I give you a circular region, what are you using? For sure, pretty much. If it's not circular, probably not using polar. Probably using rectangular because our functions work kind of that way. But for circles, goodness gracious, yes. So let's go ahead. Let's draw the projection on the xy plane. This says I got a surface. I'm above the xy plane. And I'm bound by this cylinder. Hey, can you draw the shape of that cylinder on the xy plane? Come on, what is it? What type of shape is it? Centered at with the radius of? Perfect. Is it the whole region? Yeah, because this is the xy plane. All this says is that I'm squished between the xy plane and the surface, and I'm within the cylinder coming out of it. Does that make sense? So this is my whole region. Okay, cool. Can you translate the equation that we just used to find the region into polar? I can do it. Can you do it?
Yeah.
This is why we use polar for circles, because those equations all translate really nice. If they didn't, we wouldn't be using polar. Hey, if x squared plus y squared equals 1, what else could we put equal to 1? r squared equals 1, which means r equals 1. That is, man, if you remember polar, r equals a constant gives you a circle. That's centered at the origin. That's all this stuff is doing for you. Should finish okay with that one. Now let's go and let's try to set up our double integral. This is how we start it. We don't deal with this until we have our integral completely set up. So let's try this. What are we gonna go first? Are we going to go r first, or for the inside r first, or theta first? I want you to go to your region, start at the origin. This whole thing is the region. Start there and start traversing your region. If you start hitting the shaded region first, your r starts at what? Perfect. So we're going to start at 0. Then we're going to traverse this along the direction of a radius. Doesn't matter where. You got to just go through your region. I don't care where. It's going to end up hitting your functions if you're going through your shaded region. Where do we stop? At r equals what? So you draw your picture, no problem. Change it to r's, and then your region is defined by r's. That's great. So we start at the origin. Yeah, we start at the radius of 0. We end with the radius of 1. It's a constant radius. That's fantastic. This has to be 1. So if we're okay with that. Now, is it a full circle? Let's describe that. Where's our full circle start? So we did the region on our direction first, and then across the angle direction, starting here. If we start intersecting our area, our region, right off the bat, what's our angle start at?
0.
Where's our angle end?
2.5.
Okay, now before we do anything else, can you please put the end of your double integral up there right now so you don't forget about it? It's very easy to forget about. How does it start?
R.
Let's match it up. R's first, R first. Theta last, theta last. It looks great. Is it super hard? Not when you understand the picture. And you can translate into R's. It's not bad. So we use it for circles because they're pretty nice. Done? Close to done now. What's the next thing? I didn't hear it. What'd you say? What? Convert it. Be smart about it when you convert it. Stop. Stop what you're doing. Stop. You don't just start plugging in x's and y's. Okay, you don't plug in r cosine theta and r sine theta right off the bat. Look for some easier things first. I want you to look for things like x squared plus y squared, or ways you can get it, because that's way, way, way easier. Listen, you're not looking for a whole bunch of different stuff. You're looking for the easiest stuff possible. Keep the 9. Factor the negative, and then you got something real nice. What's that going to give you?
Y squared.
Please just don't get in the habit of putting r. Make sure you understand x squared plus y squared is r squared. That was on the board earlier. That's what we're doing. 9 minus r squared. Should finish feel okay with that one. Okay, now watch carefully. This was our rectangular. Now it's our polar equation, our polar surface. 9 minus r squared. Tell me what's majorly wrong about the problem right now. This looks great. It's matched up to r's. This looks great with thetas. Something's majorly wrong. What's wrong? Say it again. You have to have those parentheses. If not, you're going to really be messing this thing up. Still okay with it? Try it. I want you to see if you can. This is a kind of a basic one, but see that you can do this. I want you distributing the r. You have 2 different little integrals here. Evaluate them and then evaluate with d theta. I hope that you know my goals for you are to get you extremely good at the setup. The rest of it, I think you can manage it. The setup is the most important part. It gives you all the power. That's what I want. Are you starting to feel pretty competent at the setup here? That was very encouraging. Thank you so much for that real boost to my teaching ego. Did you do it? Did you get some of it done?
Yeah.
Is it super hard? Not really. Not when you set it up. So if we distribute this, we get our 9r minus r cubed dr d theta. That's our distribution. That means we get 9 halves r squared minus 1/4 r to the 4th. I guess you could do a u sub too, but I think it's probably easier just to distribute that. And r goes from 0 to 1. Did you make it that far? What one do you plug in first? 0 or 1? Quickly. And then the 0, that's the nice thing about r's. 0 goes to 0, because you're always going to get an r out of that. So here we have this integral. Theta goes from 0 to 2 pi. Sometimes I don't write the theta because it's obvious that we have just that variable after this. We're going to have 9 halves minus 1/4 d theta. I'm certainly combining those fractions before I go any further, so 17/4 d theta. Yeah, I think that's probably the easiest integral we've done like ever in this class. What's the integral of 17/4 d theta? Theta. Yeah, 17/4 theta. And it matches because those were thetas. That's why we wrote them down. Where theta goes from 0 to 2 pi. And we're going to get, well, just 17 pi over 2. Yeah. Done. We're finding volumes over circular regions. It's pretty darn cool. I'd like to know if this is explained well enough for you. Tell you what we're going to do. We're going to do one more example. We're going to stop here. There is a little bit more to. There's a lot more to it. I got to show you how to find volume between two surfaces. We're going to do that over polar regions. We have quite a bit left to do, but at least we're on track. After this example, I'm going to focus mostly on the setup. We're focused just on the setup. What I'd like to do is show you a way that if you're really good at it, and you will be, you guys are going to be really good at this, you can sort of cheat a little bit. I'm going to show you that with this example, then I'll draw the region and prove it to you, but I want to show you first. So firstly, we want to find the volume below this, above the XY plane, no problem, and between the cylinders, those two cylinders. Verify that these two things are cylinders along the z-axis. What this is creating for you is like a paper towel roll. You have this big cylinder, and you have one right in between it. Do you guys see it? It's like a paper towel roll or a toilet paper roll. Big one, little one, and I'm taking that region between there. Does that make sense? Would you like to see the way to cheat at this? Here's the way to cheat. Do you understand that cylinders create whole circles on the XY plane? My theta is going, unless I cut it, my theta is going to be going from 0 to 2 pi. For sure. Does that make sense? Also, if you know how to change these those into polar equations, like pretty quick from circles, well, just go from the small radius to the big radius. They're circles. They're constant. That's fantastic. You're basically creating this polar rectangle that makes a donut, that makes this thing, this region, looks like a paper towel roll. That's all we're doing. So right now, if we wanted to, we could set this up. This would go from r equals what? What would it go from? R equals what to what? 1. Okay, 1. To r equals theta. It's creating the whole circle for us. 0 to 2 pi. I'd have an r dr d theta, and then I'd focus on doing what? Come on, doing what? What now? Converting. That's right. Can you convert this into something real nice, the denominator I'm talking about? Can you convert that? A little bit of work on that one, but yes, you can convert it. I'm going to do that in just a second. I want you focusing on the region. That's the most important part. If this went completely over your head, you're like, what are you talking about, man? Then you're the person, and it's fine, because it went over my head too when I was in your seats. That's okay. Then you're the person like me who needs to draw the region. So when you draw the region, that's a circle with radius 1. That's a circle with radius square root of 2, not 2. The region is that. That's the region. Are you guys clear on what I'm talking about here? That's the region. It's the between the cylinders. So on the XY plane, I have this picture. Show of hands, you can understand that that's the picture here. Many of you probably pictured that when you did this. But hey, how about this? Maybe the technique, you'll see the technique working for you. Start at the origin. Go in the direction of the radius, just outwards. Where do I start intersecting? Oh, come on, help me out. Where do I start intersecting my region? Is it immediate?
No.
And not until I reach r equals, which I've already changed to, r equals 1. And where's it at? That's it. This is r equals 1, and this is r equals root 2. That's where that's coming from. And then if I go counterclockwise through the region angularly, I start at 0, and I go all the way around that circle. That's the 0 to the 2 pi. That's where that's coming from. Now the rest of it, let's focus on this. If I want to change y squared over x squared plus y squared, this part, kind of nice. We get r squared. What would I have to use for the y squared? There's no way around it. You have to use it this time. What's it going to be?
R sine theta.
Say it again.
R sine theta.
R sine theta, but then I'm squaring it.
So r squared sine squared.
I always do this off to the side because oftentimes we get a lot of nice simplification here. So I got y squared, yeah, y squared. That's r squared sine squared theta because y is r sine theta. Head nod that you're with me. I know that x squared plus y squared is r squared. Do you see the simplification we're looking for? Love it. What now? What now? Integrate. With respect to what?
R.
Perfect. Do we have an R up there?
Yes.
We always have an R up there. Unless you simplify it out, you always start with an R. Always. So let's integrate with respect to R, but don't lose that R. We should be getting that 1/2 r squared and then a sine squared theta. Is that what you guys got? I need to make sure we're all getting the same thing here, yeah or no?
Yeah.
And then we're going to plug some stuff in. What variable are we going to plug some stuff into?
R.
What are we going to plug in for r?
Root 2.
Before, okay, yeah, you're right. R equals root 2 and r equals 1. Don't get in the habit of just crossing out this guy. When you plug it in, it actually matters. Do you have any questions on this or our picture? You sure? So I've shown you two ways. A way to cheat with circles. Kind of nice you did that there too. And I'll show you a way that you can't cheat. Probably next time we meet. So if we do evaluate this, we get our integral. It's only in terms of theta now, which is exactly what we want. We plug in the square root of 2. Square root of 2 squared is 2. 1/2 of that is 1. So we get sine squared theta. If we plug in 1, we get minus 1/2 sine squared theta d theta. I'd like to know if that's clear enough for you on getting that. Hey, let's be smart about it. Come on, what can you do now? Okay, let me ask you, would you integrate right now?
No.
What would you do first?
Something about it.
Yeah, let's combine them. If you got 1 of something minus half of something, you got half of something. That's just half of sine squared theta. Make it easy. Don't work too hard. You know, my dad always says that to me every time. Hey, how's work going, son? I said, pretty good. Well, don't work too hard. And I looked at him, I said, Dad, I'm a mathematician. I literally never work too hard. I always try to make it as easy as humanly possible. Why? Because it sucks to not do that, all right? Make it easy. Combine some like terms before you integrate. You get 1/2 sine squared theta. Anyone in this class, do you know how to do that? I should be able to ask any of you. Can you do that? What would I do first? Okay, pull out the 1/2. You wussed out. Yeah, pull out the 1/2. Very good, guys. Very impressive. The sine squared. Half. 1/2. 1.
1/2.
I'm looking for the sign. Minus or plus? Hey.
Yeah.
You do that, and then it becomes pretty easy. You'd actually probably do it 1/4. 1/4, 1 minus cosine 2 theta. You should be able to do this at this point after this. Then you plug in the 2 pi, you plug in the 0. If you want the answer, kind of nice. Pi over 2. End up getting pi over 2. Make sure you can do it. Go home and practice that. See that you can get pi over 2. I would love to know if this made sense to you. Show of hands if it did. Okay, cool. We're going to come back and we're going to do a lot more of this at a later time. All right, so if you recall, we're talking about some integrals, but we're finding out that for integrals that are over these double integrals over regions that are circular or have circular pieces to them, a lot of times it's really hard to do them in rectangular coordinates. A lot of times it's a lot easier to consider polar coordinates. And what that does is it basically changes rectangular equation defined circles into something a lot easier to work with. So that's the idea here. So we're going to do a few examples really quick. As quick as we can. Again, we're focused more on the setup than we are on the double integrals. I know you know how to do integrals, but the regions can be tricky. So I want to show you some very good methods on figuring out the regions. Then we're going to go on into volume between two surfaces, and then some interesting ideas at the very end of this. So let's start with this one. Let's suppose that we got this double integral over a region of y dA, and the region is this region bound by this thing and this thing. Now, I'll be honest with you, I told you this a long time ago. Your best bet to getting the region correct, that's the most important part, is getting R correct, is draw the region. Literally draw the region every single time. You can hardly screw it up if you're able to draw the region. Are you guys with me on that one? Now, that might take some knowing how to change rectangular functions into polar functions. For instance, if I look at that, I know it's a circle, but I'm also pretty good at changing functions around. If that's you too, then you'll know what to do. If not, you have to pick this up pretty quick. So, okay, well, how do I know that's a circle? Well, if we subtract this and complete the square, divide by 2, square it, add to the other side the square of this. That's completed the square, and that's a really fast method to do it. Take half the number, write it down, square it, add to the other side. That's completed the square. Now, can you see it the way I see it? Do you see that that is a circle? Yes, no?
Yes.
That's a circle shifted to the right, 1 unit. So this circle is centered at 1, 0. Everyone in class right now, what is the radius of this circle? What is it?
1.
So this circle, centered at 1, 0, has a radius of 1. And then there's going to be some pieces down here. I'm not too concerned about that. We'll find out in a second why that is. Next up. So this right here, that gives us our circle. Good to go. You guys okay with that? This part, let's also graph that. So I know you can all graph y equals x. If we graph y equals x, is that just diagonal line? It also goes through 0, 1. Can you all identify the region that we're talking about here? Head nod if you can identify the region. The region is the space contained between this line and that. So we're talking about this right here. That's the region that we want to consider. So if you feel okay with that one. Now, if we're going to go on and do this integral over region in polar coordinates. By the way, why would we choose polar coordinates here? Why is it better? Circles are nice, all right? So what we have to do is we got to translate these two equations into something that's polar. Now this one, this y equals x, that's actually one of the easier things to do. Because if we do that, we go, well, if I know that we just have this line going through the origin, then the r just goes right along that. That's fine. But I can use that to figure out what the angle is. So what's the angle of that line, talking about r theta? What would that be? 45, we always use pi. So it'd be pi over, yeah. And we could do it this way. We go, okay, well, hey, tan theta equals slope. So what it equals? 1. So theta would equal tan inverse of 1. Theta equals pi over 4. Now, the other thing we got to do, though, we have to change this thing into something that's polar. So let's try that. By the way, where you would do it, you do it right at the start. You wouldn't do it here. This is to find our circle. You do it right from the start. That's why I rewrote that. So let's try it together. If I want to change this, hey, do you remember? Come on, you guys know it. X squared plus y squared. Everyone in class, x squared plus y squared. R. So this thing, r squared equals, 2 times x. What's x defined as? Have I lost you? I don't want to lose you. X squared plus y squared, look for that all the time when you're trying to change rectangular into polar equations, because that's the nicest thing we can ever find, okay? X squared plus y squared is r squared, done. Don't go plugging in r cosine theta, r sine theta if you have an x squared plus y squared. For the other stuff that you don't have that nice relationship, like any value of x not to a power, that's where we have to start using the x equals r cosine theta and y equals r sine theta. Head nod if you guys are all right with that one. So here we go, okay, 2r cosine theta because we have x. Still all right? Tell me something you could do right now since I have r squared and I got r. So we're going to have r equals what?
2 cosine theta.
Can you keep this in your memory banks that anytime we get r equals constant, or coefficient cosine theta, we get a circle? Anytime we get r equals coefficient sine theta, we get a circle. The cosine is shifted along the x-axis, the sine is shifted along the y-axis. We're going to find that out, but that's kind of nice to keep in our head, to get used to that sort of thing. So are we okay with this so far? Yes. Now we can start defining our region. So I told you from before, the most important thing we can do is get this right and organize our integral for our best success. So let's start with that. So I'm going to create a double integral. I'm going to leave this alone. But here's what I know. If I'm doing polar double integrals over polar regions, I have to always do the dA as changing into what? RD. Good. You're not forgetting the R. That's fantastic. So R dr d theta. It's always this. It's always in this order. R dr d theta. Show of hands feel okay with that. Now, if I have the R we saw where that came from when we first introduced this in section 14.3. The dr says that whatever I'm going to do, I have to go along this region in the r direction first. And that's a little weird, but the r direction says from your pole basically, go through the region like a radius. That's what we're trying to do. So I want r equals and r equals. Remember from last time what we got to do? We got to match up that variable with that first direction. So dr, we got to have r equals. Is it making sense to you? I know we had a weekend, but it's still got to make sense. Are you guys okay with it? Now let's go to our region. Start, put your pencil on the origin, on the pole, and start going through your area. As soon as you start here, we start entering the region. So what's the R starting with? Anytime that happens when you're like, okay, I'm at the origin, I'm immediately entering into that region, your smallest R is 0. It starts at 0. Now, let's go through this region until we reach the function. No matter which way I go, here, 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 I'm going to reach this part of the function right here. Ladies and gentlemen, this is why you have to redefine any rectangular function in terms of a polar equation. Because this thing works with r equals, and all of our polar equations are r equals stuff. So if we still have this as x squared plus y squared equals 2x, you go, well, what am I supposed to put here? R. What's r? I don't know. You got to solve it. So the whole idea is, take a look at what that region is why we draw it. If it's circular, man, you're probably going to be using polar. So let's change it to polar. So change our equations into polar, and then when we go through our region, we'll actually have something relevant. So yeah, in my region, I'm starting at 0, but I'm ending with, it's got to be something r equals, I'm ending with something along this function. What is that function? Say what? So r equals 1, because this function is changing according to, okay, let me start over because I'm losing some of you all right now. Do you understand how this circle, where'd that circle come from? Where'd it come from? Did it come from that?
No.
Where'd it come from? It came from this. So this right here represents a circle. Do you get it? Did we change this into something that has r's in it? So that something with r's in it now represents this circle. So if my arrow is going from the origin and hitting the circle, use what represents the circle. So let's look up here. What function represents a circle? This one, yes. But what did it change into? Yes. Does that make sense? I need that to make sense for us to go any further. Are you guys okay? For real, are you okay with it? So here's our region. We're starting at the origin. We're going through this little sliver here. We're going from 0. Yeah, 0. Our radius is 0. When it starts hitting the area of our region, our radius is 0. And then our radius is, well, somewhere along this curve. Our radius is somewhere along this curve that I solved for. That's why we're getting the 2 cosine theta. You got to draw your picture. Change all of your equations into polar, and then go from the small r to the big R. In this case, 0 to this. That's why we have it listed there. This is that curve. Honest to goodness, show of hands if you feel okay with that one. Yes, okay, that's everybody. Now, how about our thetas? The way I showed you to do this is create your region first. Create this first. Get it all organized, r with r equals, theta with some values of theta, and then worry about the function, then worry about the integration. So what's our theta doing? I know right now that our r's are already set up, r equals and r equals. I need theta equals and theta equals. Well, what we do, we start from our polar axis, and we start going this way. So our angle, our theta, travels this way. We're traveling until we actually start hitting the region. So do I start with a theta of 0?
No.
If I did, I'd have to include that region. That's not what I want to do. What I want to do is start when I hit my region. So I have nothing, 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 nothing. Oh, I start right there. What's the angle when I start hitting that region? It's at, that's what we did that. So I start hitting at pi over 4. This is weird though. Where do I stop? Where do I stop? Well, as I traverse this, I'm going across this region, but it's getting smaller and smaller and smaller and smaller and smaller and smaller and smaller. But I am stopping at pi over 2. Can you guys see that we are stopping at pi over 2? Eric, yes, no? You guys over here? Excuse me. By the way, if you don't really need to know the intersection here, but if you wanted to find it, you would just have to set these two things equal to each other to find the 1, 1 and the 0, 0. And if that helps you, so you wanted that, like, well, let's take these. I don't care if you really write this or not, just kind of follow along. If I have x squared plus y squared equals 2x, and I have y equals x, I can substitute in for my y. With a little bit of factor, we get x equals 0, we get x equals 1. Those points, those values are where we intersect here and here. If you plug in x equals 0, you get 0, 0. Plug in x equals 1, you get 1, 1. Those are the intersection points for this circle and that line. Does that make sense to you guys? That's where they intersect. You can actually use that. So if we're going to a value of x equals 0, check this out. If we're going to a value of x equals 0, that means that r cosine theta would equal 0 for any value of r. So if r is any value of r, then cosine theta would have to equal 0. Where's cosine theta? So here's x equals 0 right here. Where's cosine theta equal to 0? It's at 2. That can also give you that angle. So by solving for those points and using that in some of our polar identities, we can find out what our angles are as well. Did that make sense to you? If you don't believe me, well then watch. I can do it a couple of the ways. Ready? Here you go. That's point 1, 1, right? What's the angle of 1? Well, the angle of that tan theta equals 1 over 1. Oh my gosh, it looks so familiar. That's right, because that's exactly how we got the slope. Do you see it? Tan inverse equals pi over 4. Done. You go, well, wait a minute. What's 0, 0? What about there? Well, tan theta equals 0 over 0. 0 over 0? Well, that's undefined. Where is tangent undefined? Pi over 2. So no matter how you do it, whether you want to do it this technique with the cosine, this technique with the tangents, just drawing the picture. That's the best way, the most intuitive way is drawing the picture and seeing what's happening. No matter what, you got to go from pi over 4 to pi over 2. Show of hands if we understand at least one of those methods. Okay, now, tell me one more thing we got to do before we start our integral. We've done the region, we have this in order, we've matched up r with r, theta with theta, it looks really good, but there's one more thing that we got to do. What is it? Good, because right now our function is what? Y, and I don't want that, I want polar. So, since y is r sine theta, all I need is r sine theta. Kind of a weird little problem, but I want to know if it makes sense. Show of hands if it does. You feel all right with it? So if you want the 20-second recap, here's the most important thing I can tell you. Draw your region. If it's circular, change everything into a polar function. So here, yeah, that creates our circle. That's why we have it here. But that creates a circle. Change it into polar. We're going from 0 to this. Use another one if you can to find some angles or another polar function. That's fine. So this line gives us that 1, 1, and the 0, 0. It gives us a slope of 1. Tan inverse of 1 is pi over 4. That's where that comes from. Tan inverse of 0 over 0 is undefined. Or cosine equals 0 at pi over 2. That's given us those two angles that we have. Yes, no? Can you do the rest of it? What's your first thing? What would you do? We're going to go through it really quickly, but I want to walk through it with you. So what's the first thing you would do here before anything else?
Combine r's.
Yeah, so we get an r squared sine theta. Then we'd integrate with respect to what variable?
R.
Perfect. And then we'd plug in for what variable?
R.
All r's. So we're going to go quickly through it, but I want to make sure you at least are with me on it. So we get our 1/3 r cubed sine theta. And we're going to plug in for r equals 0 and r equals 2 cosine theta. D theta. So r squared, yeah, add 1 divided by 3, no problem. Now, since we've integrated with respect to r, we're going to plug in for r's, and that's going to be 2 cosine theta. If I plug in r equals 0, I'm just getting 0, so this integral changes to pi over 4 to pi over 2. Then we're going to get this 1/3. If I evaluate, that gives us 8. Do you see where the 8's coming from? Eight cosine cubed theta, sine theta, d theta. What now? What would you do now? Could you, if I gave that to you on a test, could you do that? If you were working down to this far, could you do that yourself? Is this a fancy one or an easy one?
It's fancy.
It's fancy if a you sub is fancy. What's the correct choice for you?
Cosine theta.
Do it. Do it on your own. Don't do it now. Okay, do it on your own. My goal for you, and I sort of believe you, but I really want to believe you. Do you see where the picture came from and where the polar stuff comes from? That's the most important thing I can get. Show of hands if you really do, truly understand that. That's the most important thing. The second most important thing is the first step. I need to get, my job is to make sure you can get down to a Calc 1 concept, or at most Calc 2. Have I done that for you guys? Can you get down to here? From here, your u is cosine. You'd have negative 8/3 cosine cubed, so u cubed, negative 8/3 u cubed. Change your bounds, do your integration, and what you should end up with this is, at the very end, 1/6. The reason why I'm doing that and not going through the whole integrals right here, I know that, man, why don't you do the whole thing? I trust that you're able to do this to be in this class. I trust that you can actually do that, that you can do a u sub, change your bounds, do the integral, and evaluate. I'm giving you the answer so you can try it on your own and make sure you get it. Does that make sense? Okay, now let's try a couple other ones. I want to show you some things that can happen. Number one thing, one of the biggest ideas here is you got to make sure that these are actually in order, that you're going from the smallest r to the largest. So I want to try that with that example. We're just going to focus on quadrant 1 here, but I want to make sure you see something here. So number one thing, can you identify what these things are right now? Can you identify what those are?
Circle.
That's for sure a circle. Everybody, center of?
Origin. 0, 0.
Good. Radius of?
2, 0.
Fantastic. This is a,
Circle. Circle.
that's also a circle. Center, oh, do you know what the center is?
1, 2, 1, 0.
Let's find out. Let's change them. Look, if you don't know, change them into something you can work with. So here, let's use the same exact technique. Let's complete the square and let's see what happens. Are you guys seeing that? This one's pretty easy. It's a circle, center 0, 0, radius of 2. This one, well, get everything to one side. Complete the square. Divide this by 2. Put it there in a square, same sign. Square that number and add it to the other side. That right there is the circle. Now, can you see the circle? Yes, no? What's the radius of the circle? Come on.
1.
Perfect. Centered at
0.
This is shifted 1 unit. So if I'm going to graph this, hey, we don't really need to graph regions, do we, in this class? Do we? Nah, don't even worry about it. All right, you got to graph the regions. Now, I'm just in quadrant 1, so I really don't care about the rest of it. I'm going to graph this one. This is a circle that's centered at the origin with a radius of 2. It looks something like that. For real, head nod if you're okay with that one. Yes, no, yes, yes, yes. Guys over here. Now this one, that's also a circle, but it's centered at 0, nothing's being added or subtracted. 0 for the x, opposite, 0 and 1. Whenever we're shifting, we always go in the opposite direction of whatever's in our parentheses. So if we have -1, it's really shifted along this axis in the positive direction. That's the idea here. Now the radius is, what's the radius again?
1.
So the radius is 1. So it's going to intersect here. And what I'm looking for is the area between these two functions in the first quadrant. Can you shade the appropriate area for me right now if I ask you to? Oh, come on, people. Can you shade the appropriate area if I ask you? Is it this area over here?
No.
I want the between. So what we're looking for is this. That's the region in quadrant 1, or just in quadrant 1 that we're talking about. Now, the first thing we did was draw the picture. The next thing we do, come on, oh, help me out. I know you can do this. What's the next thing that you would do in order to figure out something in polar for our double integrals? What would you do?
Change the polar.
Why don't you try it? Let's try that right now. Shouldn't be too bad. Tell you what, I'll take care of the really hard one for you, all right? Pretty sure that guy gonna be r squared equals 4. You're welcome. Well, not quite done. What would you do after that?
Simplify.
This other one, I want you left-siders, I want you to help me out with this. For this function, what would you start changing first?
X squared plus y squared.
And what would that equal?
R squared.
Do you have any questions on completing the square and getting that circle out of that? We okay with that one? You sure? Okay. R squared's nice, man. Anytime you get x squared or y squared, you can find it, use it. That's r squared. How about the 2y? Everyone, what's 2y changing to? Quickly.
2r squared.
Okay, we're on roll. Next step, please.
Simplify.
Now, what I want you to do right now is label both of these functions. So, which one is the r equals 2? You got to understand the graphs to do that. So, we got this r equals 2 from this. I always write them underneath, that way I know where they come from. This gave us the outside circle. Do you guys grasp that? Well, I don't want to draw that or write this next to that circle because I'm not trying to get a region in rectangular. I'm trying to get a region in polar. So let's change to polar and identify what these curves are in the nature of their polar equations. Does that make sense to you? So this gives us the outside circle, and this gives us r equals 2. Outside circle is r equals 2. Okay, for real, show of hands feel okay with that one. Now, hopefully it makes sense. It says, what's the radius of the circle? 2. Where's the center? At the origin. That's what r equals 2 means. It's just a center at the origin, constant radius. R equals 2. That's it. That's all it means. That's why polar's so nice, because with circles, it makes it easy. This one, this guy, gave us this inside half circle. That function is r equals, I know it's small, but r equals 2 sine theta. Head nod if you're okay with that one. Now, what we're going to do, we're going to try to set up a double integral right now. We're not going to have a whole lot to go with because I'm not giving you a function. Again, the key here is set up, set up, set up. So somewhere I'm going to have a function. I don't know what that is. I don't care what that is. I'm all about the setup right now. If I were to change the end part of a dA, what am I going to have for every single time I ever do a polar region in double integrals? What is it? Perfect. That means, oh, you guys are doing great. Come on, stick with it. What variable has to go first, r or theta? So I'm going to try to define my region in R first, and then in theta. Let's try to do that. So let's start with the R. Look, here's how you do it. Here's how you do it. Put your pencil at the origin. Go from that origin as if you were a radius and see what function you intersect first. This is why we write them in terms of R, because it makes it really, really easy. It's really hard if you have x's and y's and x's and y's. Read really hard as impossible, because you need this in terms of what variable? You need this in terms of what variable? So you solve for R. That's the whole point of doing this. So from right here, go, okay, I'm going out here. What do I intersect first? I'll draw a little dotted line. What do I intersect first? Whatever you intersect first, that goes here. It's your most inside function, the thing closest to the origin, closest to the pole. Does that make sense? So we're going to intersect this first. That's 2 sine theta. It makes it kind of nice because you solved it for R and you're trying to have R equals. That's why we write the R equals. That's why we try to match up that dr. It says in the R direction, as if you were a radius. In the R direction, you come across this function first. You cross your region and you hit this function second. It's also solved for R. It's just you're going to 2. You put the inside function, boom. Put the outside function, boom. And it's nice because I taught you how to write R equals. You literally put exactly what you just solved for. It's kind of nice that way, right? Kind of nice. Show of hands if that makes sense to you. Now, what's the next thing we got to do?
Theta.
We got to do our thetas. Well, if we're in quadrant 1, listen, this doesn't work all the time, but like 95% of the time. 95% of the time, if you're in quadrant 1, you're going from 0 to pi over 2. Almost always you're doing that. Occasionally it's not true, but here it's true. You can go across your whole region. Angle of 0 starts in your region already. So angle of 0. And then we're going to cross this whole region until we get an angle of pi over 2. I'd truly like to know if that makes sense to you, yeah or no. Also, if you could do a couple of things. If you wanted to find the point of intersection, it would give you this 0, 2, 0 for the x. You can use the same thing we did here. X equals 0 means your slope of this is undefined. You'd have 2 over 0, tan inverse of 2 over 0, that's undefined. That would be that pi over 2. Does that make sense? Also, I want to point some out to you. This is going to lead us to our next example, but it has to make sense. Number one thing, can I go any further with this problem right now? What would the next step be if I had an actual function? What would you do with the function? Yeah, and then we could do it. So the main thing is identify the region. Well, that's really interesting. The function has absolutely nothing to do with the region. What's happening here is we're over a region, yeah, and this function's floating up here, and we're trying to find the volume over that really weird shaped region. That's pretty darn cool. So we're given a circle and a weird circle that's shifted. We can find the intersections, no problem, 0, 2. We can find out what the polar equations are, not a problem. R goes from this one to this one over that region. We can find out what the angle is that covers it, but that is not finding the volume. That's just identifying the region that I want to find the volume over. Is that clear? That's pretty darn cool. I can't go any further unless I had an actual function. Then I'd change it to polar form and then go for it. Now, here's the other thing. This is going to lead us to our next example. I want you to look at this. This one's weird, all right? This inside circle is a little weird. Did you notice how when I go from 0 to pi over 2, I went along a quarter of the outside circle, but I went along a full half of the inside circle. Did you see that? That's kind of interesting. What that means, what we should be getting out of this, is that sometimes, even if I have a circle, if I go from 0 to 2 pi, I might be revolving around some circles twice. Do you see that? Here's 0 to pi over 2. This would be pi over 2 to pi. That would give us a full circle. If I went to 2 pi, I'd be going around that twice. Now what happens is when we do that, sometimes when we go around twice, it starts negating area or volume. Starts negating volume or doubling volume. That's not a good thing. So we got to be really careful when we define our areas what we're actually going around. I'm going to show you that with the next example. This one we did correct because we're noticing that 0 to pi over 2 covers half the circle. That's okay. We have our function defined correctly. We're good. But I want to show you with this next example. Do you have any questions before we erase it? You guys seem more awake today. Are you more awake today? Seems like you're with it. Love it. Because we're moving a little quickly, but are you getting it?
Yes.
Yes. Love when that happens. Hey, listen, this next problem, it's going to be nasty to finish, so we're not going to completely finish it. I'll show you how to finish it. The key here is what? What's the most important thing I'm teaching you? What is it?
Setup.
Setup, man. All about setup. So, I want to find the volume under I want to find the volume under that thing. Oh, for all the money in the world that I don't have, what is that thing in 3D? What is that? Plane. Hey, give me the normal to that plane. Not that it's relevant, but give me the normal to that plane. You guys remember. That's fantastic. I want to find the volume under that plane as bound by this right there and above the XY plane. So if this is my XY plane, I'm going to have some region which we are about to draw. This plane is going to cut through this thing, which is going to be a cylinder. You'll see that in a second. And I'm going to find the volume under the plane over the XY. It's under this plane over the XY plane. Does that make sense to you? Let's do it. What's the first thing you do? Every time, if I'm giving you a double integral with a region that's not fully defined between like rectangular or two functions, what's the first thing I want you to do? Draw it. Let's start drawing them. This has nothing to do with the region. It's just going to be the argument of our double integral. Hey, now that you understand that concept. It's just the inside. We'll deal with it later. Right now, the most important part, setup. So let's look at the region. It says, hey, you're above the XY plane. Well, that's pretty convenient. So let's make an XY plane. It says that you're bound by the region created by this thing. Oh my gosh, we've had it, we've seen it, you should be getting more familiar with it. You should be looking at it right now and saying, I know what that thing is. What is that thing? Circle. Shifted along what axis? X-axis. How many spots? One, actually. How would you find it if you don't remember this for your test? How would you find it? What would you do? Let's do that. So if I complete the square, we get x. I'm going to do it over here. We get x squared minus 2x plus y squared equals 0. You're probably already starting to see it if you didn't already. If you complete the square, you take this number, divide it by 2, x minus 1, you square it, and you add it. We had it circled just a little while ago. That is a circle. It's got a radius of 1. It just happens to be shifted 1 unit along the positive, opposite of this, positive x-axis. That puts us right here. But the radius is also 1.
Can you put that in standard form? Like, if you change to standard form?
Change what to standard form?
The line below.
We're going to in just a second. Yeah, I want to show you how to do that in a bit. Right now, I'm most concerned about the region. So we start with what our region looks like. Hey, it's above the XY plane. Let's draw the XY plane, no problem. I want to make sure I know what that shape is. I want to know, make sure where that shape is. And I want to make sure that if this is giving me that circle head, now that you understand where the circle comes from, just a shifted right 1, not up, not down, radius of 1, looks just like that. Show of hands if you feel okay with that one. I also want to make sure that if that's a circle, I'm using polar coordinates and I'm using polar equations. That's what I want out of this thing. So, what's your next step? If I'm giving you a circle that's given by a rectangular equation, what are you going to change that to? Do that. So our region is this whole thing. But you got to be able to change that into a polar equation. Just do polar double integrals over polar regions with it. Were you able to get on your own the r equals 2 cosine theta? Show of hands if you were. You understand where that is. Right-siders, you guys okay with it? I know you got it now. You're like, I got it now. But if I gave that to you on a test, would you be able to complete the square and give me the circle? Would you be able to take where you got the circle from and change that into polar? Yes or no? Now, do you understand that this thing is this circle? Did you guys get that? It's the same thing. So here's what's going on. If I want to figure out the volume below that plane, above this region, here's what's happening. This thing is coming out into space, all right? That plane is going to cut it. It's only going to cut at one spot. It's going to go right through that. That's why we have this conditions above the XY plane. Otherwise, it would go forever. That cylinder would go forever. So I'm cutting this big old cylinder. I'm cutting that. I'm finding the volume below that plane, above the XY plane, which is what you're looking at right now. Show of hands, you get the concept. I always want you to get the concept to understand what we're doing here. Now, let's start trying to define our double integral. How we always do this stuff. Draw the picture, define it in terms of polar if it's circle, and then we start getting our double integral from the outside in. So we start with the bounds of integration on r, then theta, then we worry about our function. So here, we normally have that. That's typically what we get. If we're changing this, we're still going to get a double integral. But if I'm going over polar regions, I'm going to have the r dr d theta. I know that if I have a dr first, which is always the case, I have to go r equals and r equals. I'm between two values of polar functions defined by r's. That's what we do first. So we look at our region, we go, okay, put your pencil on the origin or on the pole and start going through your region in any direction, it doesn't matter. Just make sure you're going through your region. What's the first value of r that we get to? It immediately starts into our region. That means that we immediately start with an r of 0. And now if you're okay with that. Okay, well, no matter where I go through that region, I'm going to end up at this far function. Well, that's weird, but that circle is defined by one function. It's r, that's why I asked you, does it make sense if you understand that this whole circle is defined by that thing? Head nod if you're okay with that. So no matter where I go through there, I'm going to be hitting that function. Show of hands if you understand that concept. That's a big deal. So what do I end with up here? You still okay with it? Guys in the back, yeah or no? You sure? Use it to draw the picture. Change it into polar. You have to change it. Because if you're going dr, you have to have r equals and r equals. Well, r equals 0 says I'm always in that region starting from the pole. It's actually intersecting the pole. And then I'm ending at the circle. Well, what gives us the circle? that is that function. So r equals 0, yes, we're automatically in the region from the very beginning of the pole to the function. The function is r equals 2 cosine theta. That's where those two things come from. Now, let's talk about the theta. That's the next thing we do. This is going to be a little weird for y'all, all right? You better be paying attention. If you blink, you're going to miss it. And I don't want you to miss this. A lot of students make a mistake by doing things like going from 0 to 2 pi on every circle they get forever. I made a point about 10 minutes ago about this guy. Sometimes our circles are completed in less than 2 pi, in less than 0 to 2 pi. Take a look at this. If I start at 0, which I'm going to start at 0, I'm going to start here, and we're going to go around. So I know my theta is going to start at 0. But take a look. When I get to cosine of 0, if I put in cosine of 0, that's 1, I get 2, I'm right here. If I put in pi over 2, hey, everyone in class right now, what's cosine of pi over 2? What is that?
0.
So by pi over 2, I'm all the way here. Does that make sense? If I put in, so I go 0, pi over 2 is already here at the origin, at the pole. If I put in pi, here's where it gets a little weird, okay? If I put in pi, what's cosine of pi? Negative 1. Negative 1 times 2 is, here's what it says. When I get to this, well, I should put that in. When I get to pi, over here, I get a value of negative 2. Are you with me? A value of negative 2. If you remember about polar, when r is negative, I flip it. It gets back over there. So cosine of 0 gives me this 2. Cosine of pi over 2 gives me this 0. Cosine of negative pi gives me negative 2 back over here. So what's happening is, as I'm going from 0 to pi over 2, I'm getting positive. But think about this. What's every value of cosine for pi over 2 to pi? Is it positive or is it negative? Cosine's positive from 0 to pi over 2, but that's negative from pi over 2 to pi. Does that make sense? So for all of these values from here to here, I'm getting this negative here, negative. I'm shooting around the circle that way. So we get a full rotation from 0 to pi. You have to be aware of that when we're doing these problems. If you go to 0 to 2 pi, you're going to either double your volume or you're going to get 0 for your volume. And sometimes it happens it happens on both cases. So for us right now, I want to make sure that you understand that we're not going from 0 to 2 pi. Are you guys clear on why we're not doing that? And the same situation here, man. We had half a circle from 0 to pi over 2. We get half a circle from 0 to pi over 2. So we get a full circle from 0 to pi. That's the hardest part. That is the hardest part, is just setting this up. Head nod if you're okay with the setup on it. Yes, no? What's your first step all the time for these regions? What should you be doing? Draw. Then what should you be doing? Change the polar. Then go R first. Hit your polar functions in order from the origin out to your functions, out through your region, and then do your angles. The angle can be kind of tricky sometimes. Like for this circle, you get a whole rotation 0 to pi. After that, are we done? Oh, come on, we're on a great path here today. What's the next thing that we would do? Change. Now let's do that. If I change my function though, functions are always defined as f of xy equals, or z equals f of xy, a function in terms of x and y. So if I give you something that's not solved for z, your first step, I think it was brought up over here, your first step is solve it for z. This is not a nice one. Here's why it's not nice. Think about this. Planes are a really nicely defined rectangular function. You with me? They're really nice as rectangular because it's very easy, it's intuitive, it's great. As soon as we start defining rectangular functions that are nice rectangularly as polar, they start getting really nasty. So this is not going to look really nice to us. We have to do it because we're using a double integral over a polar region. We're changing everything to polar, but it's not going to be nice. Tell me what happens here. What are we going to have?
C is equal to 12 minus 3x minus 4y.
Have that.
No, what's
What are we going to change that to?
3 times
Three
r
goes
cosine
cosine
theta. 2 minus 4r sine theta.
This piece is what has to go here. I'm going to run out of room. Still going to run out of room. Picture, check. Change to polar because of the circle, check. Went from r equals 0 to the function, got it. Matched it up with a dr, no problem. Didn't forget the r, cool. Understood that around this whole circle, yes, it's a full circle, but it's not 0 to 2 pi, it's 0 to pi because we get 1 full rotation in that amount of angular motion, 0 to pi. Got that matched up. Changed my function, solved my function for a dependent variable z. That's above the xy plane, that's what we're talking about. Solved it for that, and then changed every x and every y into something that is polar. This is how it should look. Show hands feel okay with that one. Now, I'm going to do it just maybe the first step for you. What would your first step be? What would you might do here? I would distribute this. I'd also pull the 4 out. So if you can follow the algebra on it. This double integral. I might do that. I might choose to factor out the 4 from these last two terms, distribute the r to the 12 and to the r that you just factored, and that's what you should get. Can you follow the algebra on that? The reason why I might want to do that, what am I integrating with respect to first, r or theta? Which one? So this is all one big old constant, and it's not affecting the dr. So I'm integrating with respect to r first, and now that you're clear on that one. So if we do that, we end up getting 6r squared minus 1/3 r cubed, but that doesn't change with respect to r. Come on, I know you know that step. Before I go on to the theta, what do I do? Okay, I need more. I need more than just one of you to understand this stuff. Number one, do you know how to integrate this thing with respect to just r? Remember, it's like an anti-partial derivative. So r is our variable, thetas are constant. So this gives us, 12r squared, but over 2. So 6r squared. Head nod if you're okay with that one. This gives us 1/3 r to the third, but that doesn't change. It's like a coefficient. It's one big fat coefficient. Call it 7, I don't care what you call it. But that thing does not change. Head nod, you're okay with that one. Now continue. What's the next thing you would do when you get this problem on your test? What are you going to do? Evaluate for what variable? Beautiful. Hey, wait, do you know what r is going between? Write it down, man. That's why we got that. What goes down here, please? What goes up here, please? Yeah, you got to plug those both in for r. So when we get this, everything should now be only in terms of what variable, what's the final variable they should be in terms of. If it's not, you've made a mistake. You got to get rid of all your r's. That's why we have our r equals first, and they should be in functions of theta. that variable should match up with that so that all I get is that variable at the end. And this should match up with the theta so I can actually plug into the variable that I get. Oh my goodness. Seriously? Wow, that's crazy. So this has to go here and here. And thank goodness we have a 0, because the 0 is going to make those r's disappear. Did you guys see it? So if I plug that in, that's 4. 4 times 6 is 24. I think I'm getting that. 24 cosine squared theta minus 8/3 cosine cubed theta, but that is multiplied by this. I love my job. You know I love my job? I love it because I get to stop right here because the rest of us count too. I don't want to do that. That's nat. Okay, here's what this is. This equals nasty. Then 9 pi. Then happy. And smiley. That's the way this goes. So,
Put that on the test.
no problem, man. 9 pi. Guess that. Yeah, seriously, the answer's 9 pi. So, no. Let's go back through for a second. Do you understand the idea of the setup? Truly understand the idea of the setup? Show of hands if you do. Do you know why we're using polar? Why?
Because it makes it easy.
Because the regions. It's all based on the regions. The function's not circular. It's not circular. It's a plane. But the region is circular. That's what makes it nicer. Do you understand that we always have r, d, r, d, theta no matter what? Do you understand we have to go r equals first and theta equals second? Do you understand why we picked the r's the way we did and the thetas the way we did? Yes or no? After that, it can get pretty nasty when you change functions into polar equations. It's nasty. But can you follow at least the first step and get down to here? After this is not fun, all right? That's half angle. This is you distribute and you have cosine to the fourth, maybe cosine reduction formula, or half angle squared, then another half angle, then a u sub, and this thing is a u sub. That's why it's nasty. But the answer is nasty, then you end up getting 9 pi. If you want to, if you dare to try it, try it. See on your own if you have an extra 30 minutes later on. It took me about 30 minutes. But try it if you'd like to. What I'd like to do right now is take a short break. Then we're going to come back and we'll talk about how to find volume between two surfaces and some more interesting ideas. Okay, so more examples. Listen, we're now going to talk about how you find the volume between two functions. I'm going to make a case that this is so similar to Calc 1, it's not even funny. If you had to find the area between two curves, or bound by two curves, you would first find the intersection of those two curves. You'd find out where they touch each other. You'd figure out which one is on the top and which one is on the bottom for that intersection. The intersection would give you the x interval. The top and bottom would tell you what you subtract one from another. We're going to do something very, very analogous in this case. So if I ask you to find the volume between two surfaces, which I'm giving you a really easy surface here, I'll give you a harder problem in a second. The first idea is, let's find the intersection. Now before we do that, I want to show you what's going to happen. You're not even looking. You got to look for me to show you. Hurt my feelings. Look, you need to find the intersection of this. You see, the point of doing this, if I find out where this function intersects this function, it's going to give me some sort of a curve. That curve is a level curve. That curve can be projected onto the xy plane. Are you picturing this in your head? They're going to intersect. It's going to create a curve. That curve is a level curve. So what we're doing here is we're basically finding a level curve and projecting it through space. Think carefully though, okay? If I project a cylinder through space, it's going to come out, it's going to hit my first surface, and then it's going to hit my second surface. Does that make sense? Yeah or no?
Yes.
Are you just saying yes?
Yes.
Let's go through it as we're going. I'll explain as we're going. We're going to find the intersection first. It's going to give us a curve. We're going to draw the curve. What that does, if I take the curve on the xy plane and I project it upwards, it's going to hit both surfaces. It's going to create a cylinder. One of the tops of the cylinder is going to be outside function. One of the tops of the cylinder is going to be the inside function. If I take the big cylinder minus the little cylinder, I'm going to get the volume between. So the volume of the outside cylinder minus the volume of the inside cylinder. Does that make sense to you?
Yes.
You'll see it a little bit better when we draw the picture. Number one thing, if you're ever finding the volume between two functions, it's the same as find the area between two functions. Find the intersection of the functions. That means you got to have it solve for z, which fortunately we have that, and then set them equal to each other. And now that you understand the concept, you have to find the intersection. So let's do that. So when we do this, z equals this, z equals 1, therefore we get this. Get your variables on one side. Get your constant on the other side, because most likely you're going to get something that's a circle if you have squares in it like we do here. So I'll be adding these and factoring 2 and subtracting 1. We'll get 8 equals 2x squared plus y squared. Follow the algebra, get everything on one side, factor out the 2. Head nod, are you okay with that one? Make sure our signs are correct. Also, before you do anything else, man, divide by 2. Now, you know it. Come on. What's that shape? What is that? Whatever shape you get, whatever curve you get, whatever function you get, I need you to draw that. That right there, listen carefully, if you get nothing else, the region is given by that intersection. Is that clear on that? That is what is happening. This intersection gives you the region, draw the region. You're not doing it. All right. Describe this for me. What is this shape that we're getting here?
Circle with a radius of 2, centered at the origin.
Okay, that's an awful circle, but it doesn't matter. Maybe now you'll picture it a little bit better. Here's what's happening. I'd like you to just stop what you're doing for a second, put your pencils down, or if you have to, but focus, okay? Here's what's happening. You now agree, because we just solved it, this surface is going to intersect this surface. Make sense? It's going to intersect it. And the formula for the curve of intersection is this. That is what the intersection looks like. It's a level curve. Do you see the level curve? It's a circle with a radius of 2. That's the level curve there. If I graph that on my xy plane, here's the idea. If that's the intersection, that's what it looks like. That's where this outside plane or outside function hits my plane. It's this circle right there. So what I'm doing, I'm going to find the volume over this circle to the outside surface, and I'm going to find the volume over this circle, a cylinder, to the inside surface. If I'm finding the volume over the same exact circle where they intersect, that level curve, then I'm finding the volume under one large cylinder minus the volume under some smaller cylinder that have exactly the same size cylinder. Does that make sense? That's the idea. That's what we're doing here. Volume of outside minus volume inside. Area of under the top function minus area under the bottom function. Area between two curves, volume between two surfaces. Very, very similar. Did that explanation make sense to you? Are you sure? Because we're about to get pretty real with this stuff. Let's get going. Number one thing, anytime we're ever setting up a double integral, which gives us volume, double integral is equals volume for us right now, the first thing we do is not to deal with the functions, we deal with the setup, the region, the dr, d theta, the r and the theta here. So let's try that. So our volume, we're going to do all the work over here, the setup's going to be here. Our volume here would be a double integral over my functions, big function minus little function, with a dA. That's how our double integrals are always set up. That's what represents a volume for us. Now we start changing this just a little bit. Okay, well, now I know that my region is what type of region? What type of region do we have? Circular regions means I want to be using, so let's set up a polar double integral. That means that I have to end this thing with
Data.
RDR. Yeah, it's got to be d theta, but I also have this RDR. That means that this outside integral's got to match up with my theta. My inside thing got to match up with my R. Let's start defining that region. Hey, the intersection gave us the region. That's fantastic. Now, when we started defining our region, we said, okay, well, the circle, this x squared plus y squared equals 4, that can also be changed into something that is polar. Let's change this into polar. Tell me what this would change to in terms of polar, please. So, that tells you what that circle is. Well, it should make sense. This has got a constant radius of 2 centered at the origin. It's just r equals 2. Head nod, you're okay with that one. Yeah, this is given by x squared plus y squared equals 4, but the polar version of that is pretty simple. It's r equals 2. Show of hands feel all right with that one. So let's set this up. What's the first two things I should have right here? What is it? Come on, you need to know it. Don't be silent on this one. Even if you make a mistake, I don't care. What's the first two things? Well, let's look at it. Start here. It immediately starts hitting our region, so it has 0. Where's it end? R equals what? That's why we put these in terms of polar. So when I hit the function, I know what I'm hitting. I'm hitting R equals 2, a constant radius of 2. So if hands feel okay with that one. Now, how about the theta? How about the theta? This is our normal basic circle, so I know to go around the whole normal basic circle, I'm going from 0 to 2 pi. You'd try it with a couple values. If you didn't automatically grasp that, you plug in 0, you plug in pi over 2, you plug in pi, 3 pi over 2, and 2 pi. Make sure that's one rotation. Head nod that you're okay with that one. Okay, so that's important. After that, oh goodness, well, that's the hardest part, figuring out the intersection, letting that intersection level curve become the region that where we're taking a large cylinder, volume under the large cylinder, volume under the small cylinder, subtracting them. Well, but wait a minute. What about the subtraction idea? Just like area between two curves, you needed to know what the top function was and what the bottom function was. Does that make sense? You needed to know that. Well, we need to know what the top surface is, the most outside, the top surface and the bottom surface, so we can subtract them in the proper order. Does that make sense? This is the order in which you do that. You don't guess at it. You wait for your region to be defined, and then if you're still guessing, you plug in a number somewhere in that region into both of your functions, and you figure out which one's bigger and which one's smaller, which one's on top and which one's on bottom. Does that make sense? Now, what's the easiest point to plug in on that region? Plug in 0, 0. If I plug in 0, 0 here, how much do I get? Good. If I plug in 0, 0 here, how much do I get? 1. Which one's on top?
Z equals 9 minus 2x.
Did you catch that? The region's easy, man. You do the intersection, you draw the circle. Cool. Set up your double integral. That's the hardest part anyway. Getting this correct is important. And then you go, well, now I'm going to be subtracting two functions. Big one minus small one. So plug in a point on the... Do you understand why it's got to be on the region? All I care about is points on that region. I don't care about outside that. So pick something on the inside of that region, plug it in. They're all going to have the same result. One's going to be higher than the other. Here I plugged in 0, 0, that's the top, that's the bottom. We get 9 here, we get 1 there. So normally, if we did a double integral, I'm gonna write it here, but it should be here. If we did a double integral, we would have the top function minus the bottom function. This was what we got for our top. And we subtract off the bottom. Hit nod that you're okay with that one. Folks, this is the piece, the top minus the bottom, that we're going to fill in here. Do it with your rectangular first if you can. You can change it to polar. I don't really care. But let's start simplifying this thing. Do you understand where this stuff is coming from, though? Truly, I need to know. Do you understand why we're subtracting two functions here? Taking like the upper minus the lower. That was the upper. We just plugged in the point we found that. That's the lower. We plugged in the point we found that's in the bottom. What could you do? What could you do? Make it as easy as possible. So yeah, combine like terms. I like that. So that means that we would have 8. What else would you maybe do? Love factor. I don't want you to start plugging in r cosine theta and r sine theta everywhere you see this when you can start finding x squareds and y squareds. Do you understand why I don't want you to do that? It's going to save you a whole lot of time. So here, if I factor out that 2, we get 8. Cool. Factor out -2, we get x squared plus y squared. Oh my gosh, how much is x squared plus y squared? What is that? So this gives us in parentheses that. Ladies and gentlemen, for real, understood or not? You sure?
Yes.
Top, bottom, yeah, subtract them, no problem. Change it into polar right here, that's fine. You could change it to polar here, I don't care where you do it, but you gotta change it to polar somewhere. Make it as easy as possible. If you can possibly get x squared plus y squared, do it, that becomes r squared. Should fans feel okay? Honestly. What's the next step? Come on, quickly, what's the next step?
Simplify.
How would you simplify it? Okay, once you're doing that, let's distribute the r, let's evaluate the integral, let's plug in 2 and 0, and then see if you can solve the rest of it. Should be pretty quick. I'm going to write out another example after you do that.
That's right.
Hello? Oh, shoot. I zigged when I should have zagged. My bad. 16 minus 8, so 8. What'd you get?
16.5.
Beautiful. What's it mean? What did you just find? Don't do math for the sake of math. What is this?
The volume between the two.
Good. Between this thing, the volume between that and that. This, oh man, what is that? Paraboloid? Yeah, it's a paraboloid, downward facing paraboloid. So that's a paraboloid along the z doing this. That's a plane at z equals 1, and we found the volume between the paraboloid and the plane. That's what we found right now. You guys okay with the idea behind this thing? We're going to try one more. We're going to do it pretty much, I'm going to have you do it on your own. I'm going to give you some, just like I normally do, I'm going to give you the example, give you about 10 seconds to do the first step, so on and so forth. Maybe a little bit more time. Let's find the volume between these next two things. Hey, what is that? Good. That's a sphere. What's the radius of the sphere? Square root of 2. Yeah, awkward. I want you to find the volume between those two surfaces. What's the first thing we do every single time we're trying to find volume? So volume means double integral. So what's the first thing we try to do every time we want to set up a double integral? What are we supposed to do first? We want to find the region. What gives us the region if it's between two functions? What gives us the region? Say it louder. The intersection. If I can find the intersection, guys, the intersection is the region. Do you get it? It's creating a level curve. That creates a cylinder that I can shoot out and intersect the intersection of these two things, take top cylinder minus bottom cylinder. That's the plan. That's the whole idea. So I want you to find the intersection. In order to do that, you have to set two functions equal to each other. There are a couple ways you can go. One way you could go, you could square both sides and make a substitution. Do you see it? That's probably the most concise way to go. You could solve this for z and set them equal. Either way you want to do that, it doesn't really matter. Me personally, I like the whole substitute in thing. So that. Do you see what I'm talking about? If not, if you're not that type of thinker, you go, man, I have to solve things for z because that is what math does. Then you go 2 minus x squared plus minus y squared, and you have that equal to the square root of x squared plus y squared. That would be the other way that do you see where that's coming from, ladies and gentlemen? Either way. In this case, you'd square both sides. You would get 2 minus x squared minus y squared equals x squared plus y squared. Okay, well, let's add this. That's 2 equals 2 x squared plus y squared. That's x squared plus y squared equals 1. Does that make sense to you? I know it's fast algebra, but you can all do that. And not if you're okay with that one. So, hey, what's the region? What's the region?
Circle.
Radius of 1. Centered at. If you were to set up your double integral, can you see that we're going to be going from 0 to 1 for our r and 0 to 2 pi for our theta? You can start seeing the regions better if you truly understand this polar stuff. If you didn't do it this way, if you didn't solve for z and set them equal, then this way might be a little easier. You'd have x squared plus y squared plus this guy is x squared plus y squared equals 2. Well, hey, here's x squared plus y squared plus another x squared plus y squared. That's 2 x squared plus y squared equals 2. X squared plus y squared equals 1. You get exactly the same thing. I don't care how you do it. The intersection ain't going to change. There's only one way we can get that intersection. Head nod if you're all right with that one. Now, every time we got the intersection between two surfaces, that creates the region. So we have something really similar to the last example. We have a circle centered at the origin, radius of 1. What's the next thing we do right now? What's the next thing we do? Come on, help me. Help me help you. Come on, help me help you. What's the next thing that we do? Change what to polar? Yeah, pretty much everything. Pretty much everything. The first thing, though, is the region. So let's look at our region to change the curve that defines our region into polar. It's typically not that hard. Otherwise, it wouldn't be a nice circle. So for us, we have r squared equals 1. We have r equals 1. This curve is r equals 1, and the region we're defining is right there. Am I still making sense to you? Let's start setting up the volume then. So what I know is our volume is going to be defined as a double integral. I have a circular region, so I'm going to be choosing to do a double integral over polar coordinates and polar equations. So I need that r dr d theta. What variable goes right here, right now? What is it? R. Match up r with dr, theta with d theta, and we have an r there every time we choose to do polar double integrals. Now, let's see if you can do it. Let's try the setup. I'm going to give you about 10 seconds. I want you to pick the correct choices for here, 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 and there. Put your pencil on the pole or on the origin. Does it start immediately intersecting your region? That tells you the bottom R. What's the bottom R?
0.
Perfect. Go through your region in any direction, but make sure it's through the region and intersect the function. The reason why we changed these circles into functions with polar equations is so that they're easy to define. It should be r equals something. If it's not, you've probably made a mistake. So, r equals 0, yes, we're intersecting the region immediately. Where does it end? So you should get 0 to 1. That's pretty nice. You don't get much nicer than that. You still all right with it? How about the theta? Well, the theta goes around a full normal circle. 0 gives us here, pi over 2, pi, 3 pi over 2. So it's all the way around. And the way we do that in this particular circle for this particular region is 0 to 2 pi. That's close to, that's almost done with the setup. We have determined what the intersection was. We used that to make our region. We defined our region as polar functions. That's fantastic. You have any questions on it so far? Question for you. Are we done?
No.
What now?
Change our function to algebra.
Before that? Say what? We have to figure out the order. You have to know which function is on top. You have to know which function is on the bottom. Does that make sense? You can only do that if you know what region you're over. That's why we do the region first. So, okay, well, what region are we over? This one. Give me a really nice point. Really nice point on the region. You plug that in, and you figure out which one's on the top and which one's on the bottom, because you have to subtract them in the correct order. So let's pick 0, 0, and let's plug it in. Let's plug in 0, 0. Ooh, you know what? It was nice to solve it with the substitution, but somewhere down the line, we are going to have this as z equals. Did you catch that? Because you need these functions in terms of x and y as your independent variables. So even if you solve it a different way, you're still going to have to take the time, just for the sake of plugging it into your integral. You're still going to have to take the time to solve these both for z. You see, our functions, when we do our double integrals, they're always set up as a double integral over region R of x, f of xy dA. They always start like that. So I always have to. You with me? So we always have to have things as solved for z. All right, so we've done that. Now take your point. Now you can plug it in. It's a lot nicer. So if we plug in 0, 0, how much do we get here on this side? If we plug in 0, 0, how much do we get over here?
0.
Which one's bigger? That one. So we have our region, we've shot it out into space, it's a cylinder. We're going to take the volume under the top cylinder, got it, minus the volume under the bottom cylinder. All we have to do is just subtract them. Let's subtract them. Subtract top function minus bottom function. Let's try that right now. So I want you to set that up, and then I want you to start simplifying. Once you've simplified it, then we put it here. Does that make sense? You don't want to start writing double integrals and simplifying in the double integral, because you have to write double integral over and over and over and over. Oh, it's really, really tedious. So the way that we normally do it is let's just take the top function as defined, z equals dependent variable equals independent variables. Top function minus bottom function. And when we have it simplified, we're going to put it right back there. Now, you tell me, are you supposed to plug in x's and y's into this thing?
No.
So let's change it. What do you see about this? It's real nice. What do you see about that? What's that going to be?
R.
Ultimately, it's going to be
R.
r. This is r squared. Square root of r squared is r. I love that. How about that? Would you want to plug in r cosine theta and r sine theta? What would you do instead? Yep. Factor that negative, that looks pretty nice. That already looks nice. That's what I want you to plug into your double integrals over polar regions. I want you to plug in simplified polar functions. So this is 2 minus r squared. Cool. Minus, hey, square root of r squared, that's r. That's fantastic. I love seeing that. This piece is what you put here. It does have to have parentheses, but that's what goes there. Listen, we just did a whole lot of math. I'm not telling you these things are easy. I'm not telling you they're quick. They don't have to be quick and easy. What I'm asking you is if I've made this make sense to you, where it's coming from, and can you picture the idea of taking the cylinder, the top minus the bottom, and getting the kind of this little weird disc thing between, like a frisbee sort of. That idea. Can you picture that?
Yes.
All right. Okay, how about this? Do you know where the freaking circle comes from? Oh, perfect. Done! Just now, after you have the circle, plug in the point, figure out which is on the top, and you make sure you have that first. Plug in the point, make sure you know top minus bottom. And you're subtracting, because you're subtracting volumes here. Show hands be okay with that one. Then, once you find out, solve for z, subtract. Once you find out what's in order, which it is, simplify, plug it in once you simplify everything. Does that make sense? From here, what would you do?
Distribute the
You
R.
have to distribute. It's going to create for you two integrals. Okay, cool. What now? Could you do both of these integrals?
Yes.
What would you choose to do for this integral?
U sub.
If you do a u sub with u equals,
2 minus R squared.
that's gone. You do a change of bounds, and then this is pretty basic. 1/3 r to the third. Plug in the r, then you plug in the theta. I'm going to give you some intermediate steps here. If you do a u sub, I want you to watch this one, okay? If you do a u sub, du equals negative 2r dr. Well, here's your r dr. That piece gets replaced with du over negative 2. Does that make sense to you? Also, I'd change bounds for sure. If r equals 1, we get u equals, let's see, r equals 1, that's 2 minus 1. If r equals 0, that's 2 minus 0, 2. Can you please watch carefully on this one? Some people make a lot of mistakes because of this. Do you understand that you don't just get to flippy-dippy these guys any way that you want? 1 is mapped to 1 and 0 is mapped to 2. That is out of order. Does that make sense? If you write them in the correct order, what do you have to do to the sign of the integral? What do you do? So I'm going to switch this and I'm going to eliminate that. Do you guys see it? That makes the integral negative. Switching this makes it another negative. Two wrongs make a right. Trust me. Negative, negative. So this would become 0 to 2 pi. Then we go from u equals 1. Yeah, I'm switching it. U equals 2. I'm switching these bounds around. It's going to make it negative. That's what's happening. This r dr is gone. I'm replacing it with du over negative 2. I get square root of u du over negative 2, but check it out. That negative and that negative eliminate. That's why we just get that 1/2. Did that make sense? Try the math magic on your own a little bit later. You're going to see that those two negatives cancel. And then we can do the normal things. You pull up the 1/2, you get the square root of u, you integrate this. What we end up getting out of this, do you need me to do the integration for you, or are you guys okay with, would you know how to continue this problem?
Yes.
U to the 1/2, you add 1, you get 2/3 u to the 3/2 times 1/2. Then you plug in 2 and 1, you integrate again with respect to theta, you're fine. This one, same thing, you get this 1/3 r to the third, plug in 1, plug in 0, you're just going to get 1/3. Then you integrate with respect to theta. And we get, on your own, you should be trying this. Four pi over 3, square root of 2 minus 1. Woo! You sure you know how to do that? I think you do. I think we've done enough of them for us to kind of worry about the setup. Like I said, some of the stuff, I mean, I just wanted to do the setup. I actually wanted to stop right here, but I gave you a couple extra things to show you, at least the changing bounds, what you can do with the negative there. So that's a little extra. My main question to you is, are you starting to feel more confident with the setup on double integrals? Because at the start, they can be just brutal. What am I supposed to do? Well, you're supposed to draw the picture. You're supposed to change it into polar. Everything R equals. And that makes your setup really, really easy. Because if I can draw the picture and I have everything in R equals, I just have to draw a little line through the region and figure out what's the first function I hit. It should be R equals. What's the second function I hit? It should be R equals. And then worry about the angles a little bit, but normally it matches up to the quadrant you're in, or it's pretty easy to find. After that, don't forget that R. Make sure everything changes into R's. You're good to go. U subs, yeah, change bounds, but it's the same stuff. Is it truly understandable for you guys? Show of hands if it is. Any comments or questions about this particular example? You sure you're okay with that from here? You should be trying it. Okay, come see me in my office or something, or math lab. If you're not making it to here, I need to see you. And take the time to do that. Now, I have another thought. We're gonna switch gears for a while. I'm gonna teach you some magic. You guys ready to see some magic? Yeah, love magic. It's magic.
As long as it works.
Yeah, it works. You have to close your eyes for a little bit. Okay. So close your eyes. See, it's gone. It's magic. No, I'm the best magician in the world if I get you all to close your eyes at the same time. This is gonna blow your mind. This is cool. Super cool. But you gotta know what that means. What does that represent? Volume. Under a surface. Over a region. Good. Now, are you ready? What does f of xy represent? Just the f of xy.
Surface.
Okay, it represents a surface, but more specifically, it represents the height of the surface over any given point on the region. Does that make sense? This is height. Now, here's the magic. Here's the magic. Do you understand that what we are doing is we're creating volume by finding the area times the height? Do you get that? Volume equals surface area of the region times the height. That's what we are doing here. So if I were to solve for area, area would equal volume divided by height. Does that make sense? Check this stuff out. Area equals volume over height. Area equals volume over height. Do you see where it's coming from? Do you see that's what that actually represents? It's the volume under surface over region is the height of every point on that region. Now, here's the magic. Close your eyes. You know how you always love crossing stuff out, and I go, you can't ever do that, no! And I put a big cut no on your paper, like 10 exclamation points, I underline it, I go, remember that? I just pulled my hammy. Ow. Dang it. Gotta stretch more, do some more yoga. Getting old. Remember how I have you, I just say, no, you can't ever cross something. Man, this is the NFL, this is no fun league. Goodness, you don't let me cross out anything. Magic. For real. He's like, no, that's not true. It's true. It's true. If you think back to section 14.1, this is the limit, an infinite sum. This is a limit of a sum. And on every single term of all those things added together, this is a sum added together. This is the height over every single one of those rectangles. If I divide that height by height by height by height by height over every single point on the arbitrary point over every single one of those, I could write that out. We could prove it, but you'd have an infinite sum of height times delta xy. Remember that? The dA, delta A, divided by the same exact height over the same exact arbitrary point. You cancel it turn by turn by turn by turn by turn by turn. This is technically not mathematically legal, okay? So it's a big fat no. But when you go back to the proof of it, it actually works. Now, what's it mean? You go, double integrals represent volume. Yeah, but you can use them to represent the area of the region. You can use them to represent the... This is how you can find the area of any region on a graph, on a 2D space. Do a double integral where you have defined the region. What number's right here? 1 dA. You can do that. That is how we can define area of the region. This represents area of the region. Now, how about this, though? You go, wait. No, Leonard, that represents volume. That's what that is. Can't be area. Area is never the same as volume. Is area ever the same as volume? This is the volume of a cylinder, correct? If you don't believe me, that is the volume of a cylinder. Take my word for it. This is the area of a circle. Let me ask you this. If this is the volume of a cylinder, what happens if the height is equal to 1? The volume is mathematically equivalent to the area if the height is
1.
What's the height? volume is mathematically equal to area if the height is 1. We're giving this a height of 1. What? Mind blown. It's amazing. The units are different. It's the units. This would be cubic units. Yeah, even though the height of 1 would be cubic. This is square units. So the units are different, but the math is the same. You find the volume of a cylinder with a height of 1, it's the same mathematically equivalent number to the area of the base of that cylinder, the circle. Did you get it? That's pretty darn awesome. Now we're going to use it. So you do got to be careful. You do have to be careful. Just like volume below the xy plane is counted as negative, just like area below the x-axis, net signed area, is counted as negative, sometimes on these polar regions, if we go around a circle twice, we can negate area or double area. Or sometimes, like on that one of these examples, we had that cosine, r equals 2 cosine, we had the circle. Because that cosine's negative for half the circle, we end up negating area. You have to be careful. So for that reason, we use a lot of symmetry when we're doing this. I'm going to show you how to do it. We have maybe 2 examples on this. We got a couple on making life easier. Just make your lives easy. And then we'll be done with our section. I know this is a killer section. It's a long section. There's so much to unpack in this section, though. The next couple are kind of shorter, so that's not saying much. It's going to be like a 4-hour section. But I'm going to show you how to put this into practice. We'll do one example, take a little break, and come back and do the rest. Find the area of the region, where the region is just that thing. Oh my gosh, do you know what? I wonder if you know this. Do you know what that thing is? That's a circle. Shifted.
3 along the y.
Not 3. Shifted. If you look back at your examples, it was always shifted half of that number. Shifted 3/2 along the cosine is mapped to what variable? X. Along the x-axis. That is that circle. Man, this goes way off. It's a nasty circle. Crap, it's an ugly circle. This is a circle with a radius of 3/2. By the way, in case you didn't know this, to find the radius of any polar circle, just take that divided by 2. It's fine. It's going to give you 3/2. I can prove it if you really want. Multiply both sides by r. X squared plus y squared equals 3x. That's x. X squared minus 3x plus y squared equals 0. Complete the square. X minus 3/2 squared plus y squared equals 9/4. Take it squared. Hey, look at that. That is a circle. It's shifted to the right 3/2 with the radius of the square root of that 3/2. Oh my gosh, that is that circle. It's nice if you know a polar circle, isn't it? It makes it really, really easy. Did you catch that?
Yeah.
Sweet. That's what it is. You never knew completing the square was going to be so handy for you, did you? Nope. That's gone. This function is r equals 3 cosine theta. This is the region that we want to find the area of. That's the region. Now let's do it. So if I want to find the area of that region, here's what I know. The area is equal to the double integral over the region of 1 dA. I don't even need a function. Why? Because I don't care. I'm treating this as a height of 1, like a plane of 1. It's going to give me a mathematically equivalent version of volume that's equal to the area. Units are different. Who cares? Just call them square units and you're good. Does that make sense? All we have to do is define the region, which you guys are really good at because we've been practicing this all day long. So let's do it. A equals... Hey, that's a circle, right? What do you use for circles? Come on, what do you use for circles? So I need, instead of dA, oh, you still got to do this. dA changes to... What happened to the function? The function is 1, so it just becomes r. You always have an r. Now, because I have the dr, I still got to match up r to r and theta to theta. Let's be careful about this. Be careful about this. Where's the r start? So r would be 0. Very good. Where's the r end? Very good. Where the r equals the function. That's why we changed these to polar and already polar. It's kind of nice. Can you just give me a head nod real quick if you're okay with this? This next part is why we're doing this example. We would love to be able to go from 0 to pi. That would do the whole circle, right? However, if we go from 0 to pi, cosine from pi over 2 to pi is negative. It's going to negate all of this area. Do you see how the area above the x-axis is the same as the area below the x-axis? Net signed area, which is what integrals give us, would subtract this area from that area. You will get 0 if you do that. So when you're talking about area, you got to use a lot of symmetry. So go, okay, well, if this is symmetrical, let's ignore this. Let's go from here to here, theta-wise. From 0 to pi over 2 and double it. Because that's going to take the top area and not let the bottom area negate it. Does that make sense to you? Are you sure? If I went to pi, it'd go the whole way around, that's true, but I'd get positive area, negative area, 0. That sucks. So let's go positive area, know it's symmetrical, and double it. Show of hands if you feel okay with that idea. You've done it in Calc 1, now it's a Calc 1 idea in Calc 3. How about the rest of it? Would you know what to do from here?
Yes.
It's probably the easiest integral we've done in a really long time. Let's start it together. So just don't lose the 2. It's really common to lose the 2. If we evaluate, notice you're always going to get an r. So you're going to get a whole lot of 1/2 r squareds out of this and plug in r's. What can you do with that 1/2 right there? Kill the 2. So now we're going 0 to pi over 2. If we plug in this for r, we're going to get 9 cosine squared theta. If we plug in this for r, we get 0. So we get 9 cosine squared theta d theta. Oh man, it's Calc 1 all over again. Maybe Calc 2 if you didn't have a teacher that went a little ahead, like I do, and showed you how to do that. Do you know how to do that? Every time you got a cosine squared, you're going to do 1/2, 1 plus cosine 2 theta. Integrate, maybe change your bounds or change it back, I don't care. But do you know how to do this? You better be freaking out of your heads right now. This is going to give you 9/2, 0 to pi over 2 of 1 plus cosine 2 theta d theta. when you do this, when you get the whole theta plus 9/2 theta plus 1/2 sine 2 theta, and you've changed your, well, you don't even have to change your boundaries, just plug in thetas. Well, you know what, we can do it, we got time. What number would you plug in first? Pi over 2 gives us pi over 2. Hey, what's 2 times pi over 2? What's that going to give you? What's sine of pi? Plug this in, you're going to get 0. Plug in 0, you're going to get 0. So the only thing that's relevant is that one. That gives us 9 pi over 4. 9 pi over 4. You go, that's impressive. We just did calculus and found the area of a circle with the radius of what? And area of the circle is pi r squared. So area is pi 3/2 squared. Crap, Leonard, you telling me you could have just done this? Yeah, pretty much. This is a lot more fun, right? Circles, y'all. Circles. They're freaking circles. If you find the area of a circle, it's pi r squared. So now we're going to do another example in a second where you couldn't have just taken the radius and then done pi r squared. But that was kind of fun because you didn't even see that coming, did you? No. It's a circle. It has to work. But now at least you see that it does work. Had you gone 0 to pi, you would have got 0. That would have been a problem. Question?
Since we use the volume to find the area, would it be units cubed or units squared first?
Units, that's the problem with doing this, is that you have to understand that when you're really finding the volume of a cylinder that's 1 unit high. That's what you're doing. That's what you're really doing. You find the volume of that little cylinder, tuna can, okay? That would be in cubic units. You just go, well, it's area, so the area of the circle is numerically equal to the area of the volume when I have 1 unit high. So I'm just going to call it square units because I know the area of the circle would be in square units. Okay, so let's go ahead. We'll take a break right now. We'll come back. I'll show you one more where you couldn't have done this. That's pretty funny. And then I'll make your lives easier. So we'll take a little break. So moving on, I promised you one more. We're now taking this double integral because we have this thing that we discovered that the double integral, if we have a height of 1, gives us the scenario where the volume equals the area of the region. That's pretty cool. So we're using it to our advantage. The idea is just identify the region and we can find the area of that region using a double integral. That's pretty darn cool because how else would you find the area of that thing if you didn't know a formula for what this actually is? So maybe there's some shortcuts to it, but it's pretty easy with the double integral. So let's take a look at it. If you don't know what these are, you're going to have to put them into rectangular functions to graph them like you normally would. So for instance, r equals 2. Well, what's r equals 2? You guys should all know that one. Circle centered at the radius of 2. So that's this actually inside piece. This purple circle. And I'm only talking about quadrant 1. This is the circle I'm talking about. So I'm going to call that right now r equals 2. If you didn't know it, you'd have to do x squared plus y squared equals 4. And then you go, oh yeah, if I square both sides, you get x squared plus y squared equals 4. That's a radius of 2. Head nod if you're okay with that one. That's that. That's more difficult. This one, if you want to look back into your, I think it's section 10.4, something like that, of Calc 2, where you learned about graphing polar functions. What this thing is, do you remember what that shape is? This thing, this r equals 2, parentheses, 1 plus cosine theta, it gives us this, this thing. What is that? Cardioid. It's more like a butt. Anyway, it's really a buttioid. No, you can't. That's inappropriate or whatever. It doesn't really look like a heart to me because heart's like, but whatever. It's a cardioid, right? So it's a cardioid. That's the name of it. Just being funny. Hopefully, yeah, I made a butt joke. Big deal. It's a big cardioid. Cannot lie. Anyway, this just went downhill. I just pause. Just enjoy that for a second. Come back. That's what this is. And I'm looking for the area between the circle and the cardioid on quadrant 1. That's what I'm looking for. If you're able to draw the region, it's a lot easier to figure out your double integral. Right now we can figure out pretty quickly. If this is r equals 2 and this is r equals 2, 1 plus cosine theta, then we can easily go from the inside to the outside function with respect to r. And now that you're okay with that one. Now, what if you didn't know the pictures? Could you still do it? The answer is yes, I'll show you a way to do that. Here's the way you do that. Number 1, we work a little bit backwards. If you understand that you're on quadrant 1, the thetas almost always go from 0 to pi over 2, and they're going to go from 0 to pi over 2 here. Does that make sense to you? That's where they're going to go. So, if you did, let's pretend this isn't here. I'm going to stand right in front of it, so you have to pretend this. So, if you knew you were going from 0 to pi over 2, I'm not going to write anything down for this, you just got to listen. If I knew I was going from 0 to pi over 2, I could plug in an angle between there, and it would tell me what's the inside function and the outside function. For instance, plug in pi over 4. If I plug in pi over 4 here, I'm always going to get 2. If I plug in pi over 4 here, I get root 2 over 2. You follow? 1 plus root 2 over 2 plus 2, times 2, is larger than 2. I know that this function is outside that function from 0 to pi over 2. Does that make sense? Also, you could figure out that, so plug in pi over 4, you tell this one's the outside, this one's the inside. You could also tell the angle of intersection. Notice that, the angle of intersection. If you set these guys equal to each other, divide, subtract, these things intersect when cosine theta equals 0. Hey, everyone in class, where's cosine theta equals 0? Theta equals, that's showing you the angle where they intersect, pi over 2. So you can find out some really relevant stuff from this by just doing a little bit of plug in a number in the region, on the quadrant, set these things equal to each other. So you can do that. But obviously it's easier if you draw it. So let's go ahead, let's set up the area. Area is a double integral over the region and then dA. So if it's a circular region or it can be defined in terms of r, that's a pretty nice thing. What's our dA changed to? Pretty much for the last time, what's it changed to? Is that getting burned into your mind here? You're never going to forget the r now. I told you at the beginning, don't forget the r. Probably never will. R has to go here, R has to go here, theta has to go here, theta has to go here. We did talk about this. We got to have the R first. So we start with your pencil on the pole, and you start going until you reach a region. What's the first function of R you come to when we hit our region? What is it? Then that goes here. What's the last one we come to?
R equals 2.
That's why you have in terms of R, that's why they're in this order. That looks pretty nice to me. Show of hands feel okay with that one. Now, we are in quadrant 1. 99% of the time, it's just going to be 0 to pi over 2, almost always, and it is here as well. We're going from an angle of 0 all the way to an angle of pi over 2. That's our double integral. That's it. Can you go from here? Try it as I write down your next example. Oh wait, I already did. Crap. Okay, I'll give you about 20 seconds. Try at least the first step. I just want the first step and then we're going to stop. We don't have time to do the whole thing right now. This is all I want to know. Were you able to follow the setup and do the first step? Show of hands if you were able to do that. Please notice something about this. When you plug in for R, it's a little nasty. You're going to have, this is why we're not doing the next step, okay? You'd have this whole thing squared. You'd have 4 but then this thing is going to be squared. You see it? You have to distribute that. Also, you're going to have to plug in 2, and it doesn't go to 0. So you're going to end up getting this minus 2 at the end. So that's all relevant. Give that a try on your own. I don't think I did the answer on that one. I just wanted to make sure that you saw the setup, make sure these things are in order. Is that well enough explained for you? Now, the last bit of this, a little bit extra, we're going to use polar coordinates, polar equations, to make our life easier with double integrals. You see, sometimes people set up double integrals and they really screw them up. Or they don't see the region appropriately. So I want to look at this thing, and we're gonna try to make this a little bit better. Here's the impetus for the problem. So you look at the problem, you go, hey, let's give this thing a try, and you go, hey, let's do a double integral, 1 over 1 plus x squared plus y squared dx, and you go, try it for like 10 seconds. Could you do it? Could you do it? If I asked you to do the integral of 1 over 1 plus x squared plus y squared with respect to x, could you do it? What would you have to use? U sub wouldn't work because you get 2x. That's a constant, right?
Yeah.
So if I add that and that, I would get a constant, something you could call a square plus a square. That right there is a tan inverse. Do you see it? Do you want to use tan inverse? I don't either. Especially because this plus this would be a square root under that squared. That would get pretty darn nasty pretty fast. And then I'd have to plug in for something else and do integrals with that thing in there. Does that make sense? I do not want to do that. So let's see if we can make it better. Here's how to make it better. You start by defining your region, seeing what variables are what, and drawing a picture of. Are you starting to pick up that the first thing you should always do is draw a picture of your region? Every single time. So let's try that. Everyone in class, right now you are at this point, what variable needs to go right there?
X.
Why? How do you know that? How do you know it's x? How do you know? That's how. Right there. And none of you are okay with that. Now, that's going to tell us a lot. What else? What variable is this one? That's going to tell us a lot. What I want you to do is write down what x is equal to and what y is equal to. So from this, we get x equals square root of 1 minus y squared and x equals 0. That has to mean something to us. Let's try to graph that. Let's try to graph it. Here, look at the board here real quick, okay? Look at the board. Let's try to graph that. Here's how we're going to do it. Start with the easy stuff and put that on the board. Do you know what x equals 0 does? What's it look like?
X-axis.
It's not the x-axis. That one. Hey, do you know what that is? It's a half circle. Why is it not a whole circle? Because it doesn't have that little minus to it. If I were to do this, square both sides, you can probably see it a lot easier right now, but that says that's the whole circle. Does that make sense? If you were to go backwards and solve for x, you'd have x squared equals 1 minus y squared, and when you took a square root, you should have got the plus and minus there. Does that make sense? But they're not giving us that. They're not giving us the minus. So it's a right half circle. In fact, you could see that it's, radius of, did I lose you? I don't want to lose you here. Square both sides, and if you undo it, you get this right back again. I'm just proving to you that this is a right half circle and not a left. Okay, it's a right half circle with a radius of the square root of that number. Radius of 1. Okay. That's what gives us this. X equals 0 gives us this. So what these people did, look at the board. We also had y equals 1 and y equals negative 1. Look, this was the region. How they defined it was this way. Let's see if it makes sense. How they defined it was they went from x equals 0 along the x-axis. This should all be ringing a bell. They went along the x-axis from x equals 0 out to x equals square root of y minus 1. Can you see it? Can you read the problem from this picture? Then they went from y equals -1 across the region to y equals 1, and they used rectangular to do it. That's the original part. Is it going to work out well? No, that's a bad thing. What we want to do is this. What we want to do is redefine this region using polar, and let's see what happens. It's probably going to be better because what shape is that? So let's redefine this. Let's erase these marks because that's what someone did, and they kind of messed it up. This was someone who didn't understand polar. This is someone who said, "Hey, I got a circle. What are you going to use? Rectangular." No, that's hard, man. That's hard. So let's start redefining what this shape is all about. All we need to know is what gives us this curve, and we can find it right there. Notice I get this from that, right? Can you all redefine that in terms of polar? I know that you can. What is it? So we start changing pieces. Instead of using a function x equals square root of y, no. Let's call this r equals 1. Well, that's already a whole lot better. Does that make sense? Okay. If you were to set up your double integral, I know I'm going to leave my function alone for right now. All I want to do is be able to change this dx dy. Everyone in class right now, what's this dx dy have to change to? I have to always, for polar regions, go from R to R. So let's look at our region. That's why we draw it. Look at your region. Start at the, and by the way, your region is this whole thing. We already talked about it, but if you need shaded, that's your region. We start at the origin. What's the smallest value of R that I get? Where does it end? 1. No matter where I go in my region, hey, it's a circle. We get 1. That's cool. Should fans feel okay with that one? Now, your theta. Because we're using polar as dealing with circles, our theta is oftentimes kind of intuitive. Once in a while we get something screwed up, especially if our circle's shifted. But from right here, can you tell me where our theta's starting and where our theta's stopping? Theta's starting down here. And it's going always counterclockwise, here to here. Where's it starting? Don't use 3 pi over 2. You can't go 3 pi over 2 to pi over 2 because that would be going this way. You have to go from negative pi over 2, always moving counterclockwise and going positive. Negative pi over 2 to pi over 2. Yes?
If we wanted to, instead, could we go from 0 to pi over 2 and multiply the whole thing by 2? That way we don't ever have to worry about the negative?
Only if you know the region's symmetrical. Only if you know the function over the region is symmetrical. And I don't know that here. Okay, so the region, it's not just about the region itself being symmetrical, the function over the region would have to be symmetrical. Because right now, we are finding volume over that, okay? This is not an area problem like before. This is a find the volume of this function over this half circle, right half circle, and I don't know what that's doing up there, okay? So I can't do that. What I can do is define my region appropriately, understand what the theta does. Show of hands if you feel okay with that one. All right. Now, could you have maybe done it a little different and got these values? So like, I really don't get this. You go, well, you can, but you got to be very careful. So if you don't understand why it's negative pi over 2 and why it's pi over 2, you can use this. If you have y equals 1, hey, what's y equal to in terms of polar equations? What's y equal to in terms of polar equations? Then r sine theta would have to equal 1. Only wait, at the endpoints where I'm trying to get to, the r is 1. Do you see it? The r would be 1. So this would be sine theta equals 1. Oh, hey, how about that? Sine of what angle gives you 1? Pi over 2. Shows it to you. Do the same thing down here. You go, okay, r sine theta equals -1. But wait, the radius is 1. Radius is not negative down here. Radius is just 1 down here. So sine theta would equal -1. Hey, sine of what value gives you -1? Negative pi over 2. You can't go this way. You got to start down this way to make this continuous region. But it would be negative pi over 2. That's how you can get those as well. So just two ways. The picture obviously is easier. It's easier to do that. Depends for the right with that one. Now, how about this? Once we've determined this, I'm going to have to erase it. Are there any questions on that? After we've determined polar, where we're going, now we deal with the function. I want you to change the function right now. Give about 10 seconds. It shouldn't take long. So change this function into something that is polar. What'd you get?
R over 1 plus.
Okay. What are y'all using? For sure. What's the u?
1 plus R squared.
So you're going to get 1 plus r squared is your u. Du is that 2r dr. You're going to get a 1/2. R dr gives you that du. Probably change your bounds here. Then when you integrate, well, you can do it if you want to. Do you guys want to do this one? Okay, why don't you give it a try? Finish that off. I'm going to do it here in a little bit. We'll write down our last example for this section. Let's see, we got 1/2, r dr is our du. So we're going to have that 1 over u. Integral of 1 over u du is ln absolute value u. We're going to drop the absolute value. Do you know why?
Because it's squared. So
It's squared. Because when I plug in these values, that's always positive. It doesn't matter. So, and you can just plug them in and it'll be fine anyway. So this is going to give us this 1/2 integral negative pi over 2 to pi over 2. Plug in 2. Ln of 2 is ln of 2. Ln of 1 is 0. kind of an awkward little problem. You have a constant. Is it okay to integrate a constant?
Yes.
Sure. And what we end up getting out of this is, well, 1/2 ln 2 theta evaluated from negative pi over 2 to pi over 2. Plug in pi over 2, subtract negative, it does not go to 0, it just goes to pi. That's it. So you're going to get pi over 2 ln 2. Done, that's it. It's a little weird. That's it. Now, what is that? What is that? Is that an area or is that a volume? What is that one? Be careful. What is that one? That's a volume under this surface over this right half circle on the xy plane. Should eventually be okay with that. Now this one's super weird. We're gonna go quickly through it, but I want to show you how even if we have a rectangular region, sometimes it benefits us to do polar instead of rectangular, depending on what the function is. So check this out. Look! I need your attention. Come on. We got about 20 more minutes, and I need you. This nasty, real nasty. Why? Because if you were to do this with respect to y, you definitely have a trig sub. Do you see it? In fact, you have, that would be the side of a right triangle. You'd have a leg of x, you'd have a leg of y. You go, okay, well, that means you're going to get, I don't know what you're going to get, freaking trig sub. That sucks. I don't want to do that. Let's make it better. Let's make it better. So how we make it better, what do you do? Every single time you get an integral, double integral, I don't care what you're going to do with a double integral, you're going to do what first? Let's draw the region. So what I know, because dy comes first, that means that this is y equals, and this is y equals, and this is x equals, and this is x equals. Let's put those all down. Y equals x, y equals 0, x equals 3, and x equals 1. So if I graph all of these things, it's going to give me the region. Y equals x looks just like that. Y equals 0, well, I have y equals 0. It's just the x-axis. X equals 1 is a vertical line, as is x equals 3. The region we're looking at is this guy right there. And now that you're okay with that so far. Now here's the awkward part. The awkward part is, if we're going to use polar equations to represent this, we've got to change these lines into, and let me show you why. We've got to change these lines into polar equations. Check it out. You're not checking it out. Check it out. If I started here and went through my region, I'm first going to come to that line. I need to define that polar. Then I'm going to go through and I'm going to come to that line. I need to define that as polar. So we're going to do that. It's not that hard, it's just a little weird. Hey, let's go over here. X equals 3. Can you tell me what x equals, don't say 3, what x equals in terms of polar? So I know from here that r cosine theta has to equal 3. Hey, every polar function needs to be solved for r. Let's solve this for r. Now you tell me, 3 over cosine theta can be written better than that. Instead of 3 over cosine theta, you should write this as 3 secant theta. Using the same logic, if this one gave us r equals 3 secant theta, this one's going to give us r equals... Let's redefine our region in terms of polar. What I know right now is this first guy I'm getting to, this first line, can be written as r equals secant theta, and this is r equals 3 secant theta. Head nod if you're okay with that one. That's practically enough. We're almost done. I'm going to leave some space. I'm going to write r, dr, d theta, because I know that's what we're going to end up going to with our polar region. I know I need to go R equals to R equals. Okay, let's try that. When I'm going through my region, ladies and gentlemen, starting from the origin, what's the first function of R that I hit? Perfect. What's the last one that I hit? That's excellent. Now our thetas. If you're able to draw the picture, the thetas are very intuitive. Look at the region. Look at the region. I'm starting with an angle here. What's that angle?
0.
I'm ending with an angle here. What's that angle?
Pi over 4.
Pi over 4. 0 to pi over 4. Do you guys see the 0 to pi over 4? Goes this way. Now, what if you're like, Leonard, I'm not intuitive. I don't have any intuition at all. Yes, you do. You can see the picture. You can do the angle. But if you're like, no, I don't understand that at all. Well, then you use these as slopes, and you do stuff like this. If y equals x, the slope is 1. Do you guys see the slope? Tan theta always equals slope. Hey, where's tangent theta equal to 1? The angle of the the slope of a horizontal line is 0. Where's tan theta equal to 0? 0. That will also tell you 0 to pi over 4. Head nod if you're okay with that one. Now, what's the next thing we do? Come on. Next thing. Next thing. Function. Okay, let's do it. What's that going to end up being?
1 over r.
1 over r. Squared r squared. 1 over r.
And the r's cancel.
I love it when r's cancel. That's why I became a math major, to make sound effects. Best part of math right there. So if I eliminate my r, oh wait a minute. If I eliminate my r's, I have 1. Can you still integrate with respect to r? What are you going to get? You have to have something to plug in r's to, so you got to get at least an r. So we're going to get r, and we're going to evaluate it for r equals secant theta to r equals 3 secant theta. D theta. Hey, would you tell me something? Would you integrate this right now, or would you simplify this right now?
Simplify.
Please do that. Don't make your lives harder than they have to be. If we integrate that, we get 2 ln absolute value secant theta plus tangent theta and absolute value from 0 to pi over 4. If you think back to all your trig sub days, you do a trig sub on that thing, you're going to end up with a secant. That's what you're going to end up with. And then you're going to have to evaluate it again. You're going to end up with integral of a secant or something. And you're going to get ln absolute value secant theta plus, if it's even possible, that's what you're going to get. Just like all the trig sub that you did before. If you do evaluate this, that 2's there, and we get natural log square root of 2 plus 1. That's what it gives you. That's a little bit nicer than trying to do trig sub on that stuff. Defining your, even though it's rectangular, if your function fits better in polar, you try doing that too. So change a region in polar, sometimes you get some really nice stuff out of it. What's it represent again? Is this an area or a volume area? It's a volume. Under that, that surface over that region. That's the idea. So, Vincent, makes sense? Pretty cool, right?